Yes, hello, good morning all. Yes, Sanjay, am I audible?
Yes, Saurabh, you are audible.
Yes, good morning all. This is Saurabh Borsate, Acting PG Secretary and Associate Head PG Academics, Academics and Career Council. Welcome to the session. Hello, good morning all. Yes, Sanjay, am I audible?
Yes, Saurabh, you are audible.
So, I first want to introduce our first expert, Mr. Sanjay Singh Tomar, Y17, PhD scholar, IIT Kanpur. He is a PhD student from the stream Structure Dynamics and Aeroelasticity, Department of Aerospace Engineering, IIT Kanpur. Before this, he has finished his Master of Science by Research from the Department of Mechanical Engineering, IIT Mandi. He has about 6 years of experience in the finite element modeling. His current research interest includes finite element modeling, composite structures, impact modeling and analysis, functionally graded structures, etc. Okay, he will be cover the three important topics, that is introduction to FEM and ABAQUS GUI, basic structural modeling using Abaqus CAE, and performing FEA analysis using Abaqus CAE. Okay, so this session will be from 10 to 12:30. Okay, so after this session, we will go for the question and answer. So if you have any questions, please put your question in the chat box. Okay, and those who are the YouTube live, please put your question in the comment box also. Okay, so after the session, we will take your questions for the expert. Okay, so I request to the Sanjay to take over the mic and start your session.
Thank you, Saurabh. Good morning, everyone. Firstly, I would like to thank the Saurabh and the Academic Council to provide me this opportunity to express my knowledge with you guys. So firstly, let me share my screen once. Okay, so I hope everyone is able to see me. Okay, so before I start with the topic, I would like to tell you guys that how things will be going in this session. Firstly, I'll be explaining you about the basic modeling and FEM structure, that how modeling is done with the help of FEM. Then I'll move toward slowly. I'll explain you that how Abaqus environment can help you in solving the structure analysis problems. So basically, today's topic is about the introduction to finite element analysis using Abaqus CAE. These are my presentation outlines, and the brief introduction to FEM will be the initial, as I have already explained it to you. Second will be I'll explaining about introduction to Abaqus CAE. Then I'll be explaining some basic advantages of Abaqus as compared to the other GUIs. Then I'll be briefly explaining about the Abaqus GUI, that what is it, what are the things which are possible. And then we'll have the demonstration that how things will be going, how we can model things using Abaqus. And then I'll have present you some examples and some benchmark studies which I have done to demonstrate with you guys. So starting with the basic finite element analysis. What is it actually? We basically have a physical problem which we try to model and get the respective response, or we try to calculate the dependent or any type of variable of interest. So let's say we have a bar. Okay, that bar is getting extended about its length. That's our physical problem. So that physical problem, what we do, we always try to represent it in terms of some governing differential equation. So let's say in this case, in the case of bar, that governing differential equation will be a second order ODE. Now that ODE will be approximated using finite element analysis. As in finite element analysis, we have a weak form. Then the condition on we apply the condition on the weak form to get the respective shape functions, or we decide the element. We break the domain into the respective number of elements to get the respective stiffness matrix or the force vector and calculate the respective displacements. for fluid problems or the heat transfer problems, fluid problem we are interested in the velocity field, and the heat transfer problem we are interested in the temperature field. So studies are actually analogous. So this analogy could be maintained in the respective sections. Then once we solve for the basic finite element equation, we try to post-process it to get the final post-processed quantity. For example, let's say in structures we have stress and strain and reaction forces and many more things. So let's start with the today's software, that is Abaqus CAE. So Abaqus CAE is a common graphical user interface which is used for modeling and solving the basic finite element problems. Nowadays, it has been widely used. A large number of researchers throughout the world has been using it. This basic Abaqus solver this Abaqus for struct, actually I'll be covering most of the structural part, but it has all the electromechanical or the CFD domains also. You can use them if you are from that domain, but I'm from belongs to structure scope, so I'll be more focusing upon the Abaqus standards, which is an implicit solver, generalized implicit solver, and Abaqus explicit, which is a solver which contains the which actually based upon the wave propagation, which is very helpful for dynamics and wave propagation problems. There are other packages such as LS Dyna, COMSOL, Unigraphics, or ProE. So a number of packages are there. But what I have found is Abaqus is very user friendly, and the basic advantages of Abaqus, which I have found it out in last couple of years, is that it has a very nice nonlinear solving capabilities. For example, if you have a nonlinearity in your problem, such as such as you have plasticity or any other, for example, you have a contact or you have a crack, this crack singularities, or any other displacement nonlinearity, large deformations, this could be easily handled with the help of Abaqus. So it has contact modeling capabilities. As you all know, contact is a very tough problem to solve. It's not that easy that like a very small, it's not like a small deformation problem that you can solve it right away. You have to make a lot of, you have to take a lot of pain to solve such problems. So Abaqus provides you such working environment with which you can easily able to solve it. I think in the second session, Samath will be taking contact problems. So it has a very simple, third advantage is that it has a very simple and efficient work environment. You can, I will discuss it once I'll go there. Fourth point is that it supports multi-physics like COMSOL. COMSOL also if you have used a few of you might be using COMSOL also. It has a multi-physics option where you can club the structural and CFD or electromagnetics problems. It can be used for finite deformation or large deformation problems. That is very tricky, because in such problems, if you are these problems are the problems where actually the capabilities of the softwares are being checked. For example, where for example, where if you consider a failure problem where the body is getting elongated for a very with a very large deformation, and it is getting failed. So such problems can be easily handled. For example, milling operation or the milling operation or any production operation where chips are getting formed. So such problems can also be handled with the help of Abaqus. We can handle fracture and damage modeling. So any structure usually have a sort of inherent damage, and such damage modeling can be easily handled with the help of Abaqus. And it also, one of the most important feature with Abaqus is that it supports the a very good developing support. For example, say scripting and using subroutines. So it is supported by Python scripting. All the work which I'll be showing you, it will have a background code will be parallelly generated, and you don't have to take pain to do each and everything again. You can work on that code too and get your parametric study and make a number of studies in that loop. Along with the subroutine is a very Writing subroutines is also one of the best features of the Abaqus. I think LS Dyna also support the similar subroutines. The subroutines can be written in Fortran, and these subroutines can be used to add the respective models. For example, for models to add certain capabilities. For example, it does not have the let's say third order element in the third order shape function. It does not support, or the third order element this does not support. So with the help of UVL subroutine, you can add the third order element in the Abaqus, and you can perform your modeling and get the answers. So let's now talk about the basic system of units which Abaqus has. Like our basic coding, okay, any basic FEM code, Abaqus does not support any system. You just have to be consistent throughout your study. Let's what I always try to do, I always try to consider MK system rather than rather than changing things from one system to other. Some people try to take the one second, I'll turn on the pointer. Some people try to use a SI system, but changing it into tons and calculating all the quantities into different systems sometimes create number of issues. So always try to stick to one system. So I have provided this table in case you want, you can save it for your future. Next, now let's come to the Abaqus GUI. The basic Abaqus this is the basic Abaqus GUI diagram. This is the Abaqus viewport, which is shown in the center. Now at the top we have the main menu. Now this is a tree. The left hand side is a tree which considers the model and the results chart. The top one, in the top we have the module, model, and the part selectors. Then here we have the modeling tools. And at the bottom we have the command and message panel. Whatever you'll be performing, for say, let's say you created 10 elements, it will be shown here. Okay, so you won't have to think that okay, how many number of elements are being created. And it has a very nice help also, which I'm going to show you after some time. So let's talk about the basic. This I have created a basic block diagram for any Abaqus analysis you can use. So what we will be doing, we'll try to model a geometry, then we'll assigning it some material. So the whole procedure is actually divided into 3 basic steps. First one is the pre-processing. Second one is the solving, that you have to select a respective solver. Is it a standard or the explicit? And the third one is the post-processing. So the first is the most important step, because you have to take a lot of pain in that. Okay, so everything will be decided by this step. So initially you have to decide the model geometry, that okay, for example, let's say I'm trying to model a plate which is getting deflected. Okay, so that geometry will be our plate. Okay, let's say second, we have to assign the respective material property to the structure. So let's say that plate is made up of steel. Then okay, so once we have the oh sorry, this second step, I think there's a typo. So we'll define the material properties. In the third one, we'll assign the material property to the structure. There's some noise at the back. Saurabh, can you please check that everyone is muted? Okay.
I request all the participants, please mute your mic. Yes, Sanjay, please
okay,
continue.
so once we have assigned the properties to the structure, our structure is ready. So now what we have to assign the boundary constraints and the loads. For example, boundary conditions can be we have fixed support or a pinned support or the simply supported support. Loading conditions can be of different types. You assign a point load or the pressure load or the impact load or any other sort of loading, temperature field or and other things, fluid friction or number of loads are there. So once I'll come to that model, I'll explain it to you guys which are the loading condition which Abaqus supports. Then after we assign it, we create a mesh. Actually meshing is the basic crux of the finite element analysis, that how you are meshing a structure. Okay, if your structure is not proper and it is getting deformed, so if your problem is slightly non-linear, or say you are moving in for, say, see, for small deformation problem, number of things works very easily. But if you consider a finite deformation case, so if your mesh is slightly not, if your mesh is not proper, you're going to have distortion problems. Then, and so you have to be very careful about the mesh. I'll explain you with one example that, okay, what are the basic techniques that you can use to have a proper mesh. And then in the last, you have to define the output variables. The number of output variables are present inbuilt in the Abaqus, but you can even define it in the using SDVs, means solution dependent variable. You, for yes, in the cases when you define the subroutines, so you can have your own variables also. So that is also supported in the Abaqus. Then after we have all this, you have completed all these pre-processing steps, we decide that, okay, then we submit the job. Then the respective solver which you have selected, that might be standard or explicit, it will solve your problems. And then once you have solved your problems, we'll be visualizing the results using visualization module, and see how see our response. Okay, so before starting before starting the analysis, these are the few points which I think which are very helpful. So first thing is, do not use elements more than necessary. So why I wrote this point is because in an analysis, for example, let's say you have a workstation. Number of people, what they will do, they will just try to get millions of, well, let's say 1 lakh element they will select, and they will try to solve it. So taking unnecessary element is not going to help you, even and it will try to increase your computation time drastically. So you have to be very careful. And for in the explicit analysis, as I have already explained you, that everything will be demonstrated, everything, your simulation time will be governed by your wave speed of the material that you are selecting. So along with that wave speed, that smallest length that you are selecting in the mesh will also govern that how much time it's going to take, because in the end it's a loop which is running over the each element. So more the number of element you have, more the time it's going to take. Okay, so third thing is the perform proper time stepping iteration. So time stepping is an important thing. If you don't have proper time stepping, you won't be able to magnify your results in the respective time domain. If possible, you can use some parallelization. It supports parallelization. Check out for output variables. That, okay, see, based on your output variables, your result files will be generated. Yeah. So the more output variable you have, the largest size files will be generated. If you so always try to take those files which you actually want. For basic problems, only displacement and stresses are enough, or reaction forces are enough. So don't try to take all of them, or don't don't believe on the pre-selected modules always. Okay, and always check your mesh quality. That's I've already explained it to you guys. So now, before moving to the examples, let me show you the main Abaqus what do you say that Abaqus documentation. Yeah, that is actually very much important. So let me share it with you guys, the new screen. Okay. So what you Abaqus, so just Google Abaqus documentation. Saurabh, you are able to see it, right?
Yes, yes.
Okay. So once you will Google it, Google Abaqus documentation, you will be able to get number of documentation links. Just click it. These are the basic things which are available in the Abaqus documentation. It almost has a number of things which you can easily read, and language is also very simple. For example, let's say this is the basic user guide, where you can have how basic interact, how you can interact with the basic Abaqus, basic functioning, how you can what are the various modeling techniques are available, and all these things are listed here, the basic element support. Along with that, the scripting, I think scripting and the Just telling. The subroutines, that guide is also available here. So that this is actually a number of people who are joining, they might be interested in. So various subroutines are there. The subroutines are basically categorized into three domains. I don't know about CFD, so I'll be skipping it. If you have interest, you can explore it more. So in Abaqus standards, you have a number of subroutines which you can write it at your own. But what we are usually interested in is the UMAT, is the user material subroutine, U hyper for the hyperelastic materials, and U hard, so for the plastic materials. Along with this, the explicit subroutines. VU hard means for the dynamic problems. This is actually VU. These explicit subroutines are different as compared to the uh, implicit subroutines because the basic formulation is actually different. So you have to create your material model as per that. Okay. So and the VUMAT for explicit subroutines. Okay. Along with this, you can find even the Python scripting guide here. Right. So actually, each and everything is written in a very basic form. If you want, you guys can read it out and get things done slowly. So now let's back to the now let's move to the presentation part. I'll explain you guys about the basic Abaqus GUI. So let me again share the new screen. Okay. So this is the basic GUI. As I have already explained you, this is the basic tree. The left hand side is the basic tree where you have the all modeling and results information. This is the main menu. Here you can before you start here you can select initially you can select the basic modeling type that you want to, which type of model you have to select. Then you can directly open the ODB files. ODB is the basic the output file they are talking about. So ODB represents the output file. Then you can import the sketches, part and models. Actually there are number of softwares which are being supported in Abaqus, but this is my laptop, so I have installed few of them. So Nastran, Abaqus, you can even do that. You can use it as a solver only. Okay, you can create a part, let's say in SolidWorks, you try to mesh it with hypermesh or any other software, then you can import that file here and you can just use it as a solver also. That thing could also be done very easily in Abaqus. It is supported by a number of software. So while installing it, I think we have shared the link with you guys. So while installing, you would have gotten those links initially that okay, you want to install this documentation or not. So initially you can select those and get the various support if you're using those softwares for modeling and meshing purpose. Okay, so you can export it to other solvers also. You can select these parts. Then we can run scripts that okay, all the processes which I'll be explaining could be done. I have told you before, could be done using scripting. So you can just and you can just run that script directly from here. You can create a macro. For example, if you use Microsoft Office, it also supports macro. That okay, let's say you want to create one document and again you want to run it, so you can create that macro script also here. Then print is to get the output. Okay, so now let me show you the various modules. So I'll start with the explaining various modules. So this is the part module. Here you have this create part with which we can create parts. It supports 3D, 2D planar and axisymmetric options. The type of deformation or the type of structure you want to create. Eulerian is basically mainly used for fluid guys, analytical rigid and discrete rigid option if you want to create some rigid part. And along with that, if you how you want to create that structure using solid, shell, a wire or a point. So all basically these four covers all sort of structure which are present. Okay, these are the various extrusion options. Shell option is there. Cutting means how you want to cut it, round and fillet. These are basic modeling options which you can find in any basic modeling tool. For example, in AutoCAD also you can find it. In SolidWorks or Pro E, all these options are usually present. And these are the options which are used for the partitioning the structure. I'll come to it when I'll be explaining you about the meshing, that okay, how that meshing could help you. So the partition is actually a very best tool which is available in the Abaqus. I haven't seen in other software, but partition will actually help you to improve your meshes drastically. So I'll come to it. From here you can create your datum, add datum surface, and these are basically modeling tools which you will be using again and again to solve, to create your important models. Okay, come to the next part. These are the property. This is a property module. So actually same things are available here also, but why I'm explaining it from here, because this is a directory. Okay, one by one you can follow and you can do that. For beginners it is very nice. Once you have gained some experience, you can directly click it over here, because it can be in a help hazard way. So I'm trying to explain you from the very basic that okay, one by one module you can select and you can assign the properties. So while I'll explaining the demonstration, I'll be doing the demonstration. In that part also you guys can just follow this tree and you can solve each and everything. Okay, so now comes to the property part. Initially it has the create material part. Actually these items and these blocks are actually the manager. So you either you can select here or create new one, or you can select this one also directly. Okay, so this one is the create modeling, material modeling. So with the help of this, you can define the material properties. So in the general tab, you can even define density of the material. Depth is this is for when we define we use user subroutines, we define the number of solution dependent state variable. I already explained you initially that okay, we have some, in case you want to define some solution dependent variable, you can define it from here. Okay, then regularization is there. Then user material. If you want to give the user material properties, you can define from here. Actually, these lower options are for the user material case. The inbuilt option is only the density. Okay. Then it comes to the mechanical. In mechanical, you have various types of mechanical properties which you can have. For example, for the elastic case, we have isotropic, engineering constant, lamina, orthotropic, and isotropic, coupled, traction. Number of options are there which can be used for the various applications. So I'm just trying to generalize to you guys that okay, these options are available in the Abaqus. In the plasticity, you have large number of models. In case the model which you are trying to use is not there, so you have to write the subroutines and add that model, obviously. So for the damage, ductile damage, you have Johnson Cook model, shear damage, FLD, MK damage. A number of models are present. For traction damage, you have Quad S, Max S, Max PS model. So these are the basic damage model. For the considering damage in composite material, we have well-known Hashin model. You have for elastomers like rubbers, you have the Mullins effect. So it is actually already inbuilt in Abaqus in the new module. Then you can add brittle cracking. You can add, so the all properties are there for your basic. You can add equation of state directly for if you are working with gases. So for electrical and magnetic case, you can add all these things. You can define piezoelectric properties, electrical conductivity, and number of for diffusion also you have diffusionability, solubility, or any gel gas. So all these property you can define it in this module. Okay. Now once we define the property, we have to create a section. Actually, in the Abaqus, this thing is actually different as compared to other software. In this, we define a section and we assign that section to the structure. Not necessarily that only 1D structure you have to define a cross section. For 3D structure also you have to define the section, because it is generalized. So for each and every structure, you have to define a section and assign that property. With the help of this, we will be assigning the properties to the structure. Okay. Then it is there the assign material orientation. For example, your material has more than one directional property, so you can define it using this. Then you can create a profile. For example, for a beam structure, you want to create an I section or a rectangular section or a hollow section. So I think all those options are available here. You can define it and assign it to the structure. Okay. Now let's move to the next module. After creating part, you have to create the assembly. Okay, so you have to currently we haven't created any part, so there is no assembly. So you have to create create instance and add it to it. Okay. Now after this is an important module. I would say this is one of the most important module among all. So initially here we create a step. This step will actually decide that which type of solver you are using. So various solvers are there as per the various application. For basic static problems, you can use static general. For very infinitesimal slow process, small deformation process, you can use that. For dynamic case, you can use dynamic explicit or dynamic implicit. For frequency, for example, modal analysis or the buckling analysis, you can use the linear perturbation. So almost all mechanical engineering, I would say, almost all structural engineering solvers are present, which you can use. Now this is an important thing. This field output variables. That okay, which sort of variables you want to decide. So actually, it is not opening it up because I haven't created any step. All these things are dependent. So once you define step, because in that step only you will be in that time domain only you will be defining the outputs. Okay, so these all are related. So once I'll be solving the problem, I'll be explaining it to you guys. The in the field output and the history output dependent variables. So these are actually the dependent upon the how you are solving the problem, how they are growing with respect to time. So you can decide those variables here. Okay. Now let's come to the interaction. For example, if your interaction will be there when you have one or more part. For example, you are trying to model an impact. So, okay, so you have to define that how one body is getting interacted with the other body. Okay, for example, you want to try something with the foundation. Now you have a foundation, you have to define the interaction. So in that cases, you have to use this interaction modules. Then next comes the loading. Okay, so once you have defined all that, you have created a model, you have defined this step. Now you have to give the load in that respective time step. Okay, that my load will be acting on this in this time zone. So okay, so I think in order to explain it to you all these, I have to take an example now. Yeah, so let's move to our first example. Once again, I'll share with you that screen. Okay, so this is our first example. What I'm trying to do is let's calculate how that a one-dimensional beam is getting bended. Okay, we all, I think, or most of us usually knows that okay, if there is a cantilever beam and if it is having an end deflect and load, how it is going to get deflect, and we will compare our output with the standard known output. That okay, what I'm trying to actually show you guys is that okay, this is basically called the benchmarking. That okay, if you know something and you are trying to check that okay whether it's working or not, let's try it out and see that okay it is giving us a good result on it. So currently I'm considering aluminum material properties which has elastic modulus of 70 gigapascal and Poisson's ratio of 0.3, and currently it will be an static analysis, so density won't be required. The cross section is of 0.2 by 0.2 and it has a length of 1 meter. I'll be applying 2 Newton point load at the top. Okay, I'll move to the Abaqus. Okay, so Before starting anything, we just have to create a working directory where we can write it. So initially, what we can do, always remember this thing: before working, set work directory to the one where you are making this where you want to save your files. Okay, otherwise what will happen, your things will be saved in the automatic default directory and it will get overwritten again and again if you haven't named it properly. So I'm defining it as the basic I have named it as beam. That folder name is beam. Okay, let me show you guys that. Okay, so once I have selected the directory, let me show you that. Okay, there is nothing in this folder. Okay, so once I so now let's actually I'll be shifting from one screen to another screen. I hope it won't trouble you guys because I want to show you how it actually works. So I'm going to this thing again. Now what I'm doing, I'm trying to save it in that beam folder. Let's okay, I have a beam file. Enter. Once I save it, sort of you, I hope you guys are able to see it. That okay, it is showing that model has been saved. So let me again go to that folder. Okay, that okay. What are the files which I generated once I save it initially? As you guys can see, two files are generated. First one is the CAE file. Actually, CAE file is a file where you are going to your drawing and everything will be sorted. And this JNL file. Let's see what is there in this JNL file. We haven't done anything, so nothing has been nothing is there at this moment. Okay. Oh, let me show you what is it. JNL. Yeah. I hope you guys can see that nothing is there. I have just saved the file. No script has been written. Now let's get to the model again. Now what we have to do, we have to define the material, we have to create the model, we have to assign the loads, we have to define the boundary conditions, and then we'll select the solver and then we'll submit the job. Okay, so let's select the part first. We have to create a part. Okay, so let's name it as B. So in the 2D planar, we have a deformable beam and we'll select a wire part. Okay, so continue. Once you will continue, you will come to this sketch section. Okay, so these are the various sketching options which are present. For example, if you want to create a isolated point or line or circle or ellipse or rectangle, or if you want to trim it, you can trim it. If you want to dimension it, you can do that. If you want to define a parameter, you can do that. So all basic sketching options are present like any general purpose software. So what we have to do, we have to create a line. Means we have to create the beam. 1D line. 1D line will act as a beam. So once I'll select one point, it will ask for create. Let me do it again for you. Once you select the line, it will ask for pick a starting point for the line. So what we can do, I'll just click it here. This is the origin. So let's just click it here. So for my first point will be 0, 0. Second point will be, let's say I want to create a 1 meter line, 1 meter length beam. So I'll select it as 1, 0. Okay. So this is my line. I hope you guys can see that. From here you can check the dimension quickly. Okay, it is a 1 meter line. Okay, then once it is done, just cancel it and click on done. Then your 1 meter length beam is created. Okay, so let's define the material property next. And I'll discuss in the same way that I'll do in the same way that I have discussed before. That okay. That beam is made up of aluminum. So let's name that material as aluminum. We are performing a static analysis, so then no need to define the density. Only elastic properties will be sufficient. So go to elastic and define the Young's modulus 70 E9. Poisson's ratio is 0.3. Click on OK. Now what we'll do, we'll create a section and we have to assign it to the structure. So there is a beam section which is already present. Just continue with it. Now here there are various options. Okay, so as we haven't decided which section you want to create, so just from this symbol, just click on it. You can decide which sort of section you want your beam to have. So currently we have a rectangular section. Says click on it. It is asking for here its dimensions. So we have 0.2, 0.2. Okay. We have created a profile. So you can have number of profile, but currently I have only one, so I have given it to the material. So if you want, you can give more Poisson's ratio, but only one, as only one day problem is there, there won't be much Poisson's ratio. Okay, so click OK. Then you have to assign this to the structure. Once you will click on assign, it will ask to select the body. So once you select the body, it will ask if you have more than one section, then you can select it from this dialog box, and then you click OK. So as you guys can see, its color has been changed. So that means the property has been assigned to the structure. Okay. Now once we have created the part, we have to assemble it. So we have only one part here. Otherwise, if you have more parts, you can always use these options. Pattern, for example, you have a number of geometries, you can pattern in circular or this option. You can translate this structure. So all these basic assembling options are there which you can select. So once you click on this create instance, what you have is the two types of parts, two types of instances types are there. One is dependent, second is the independent. Dependent means it depends upon the type part to part. For example, if you want to mesh the respective parts separately, or you want to create the whole mesh, whole model simultaneous. So you can select any option, but I always go with the mesh part option because usually we have more than one part. So okay, we want to mesh it. We always try to do different meshing. So always select I always try to select the first option. Okay. Now, once your assembly is created. So once your assembly is created, you just go to the step. And now here, general static is the basic analysis. It is an implicit solve. Actually, in this static solver, it does not matter directly. It's a infinitesimal deformation. So general static solver can be enough. Now, once you select the solver, here you have to define the time period for which you have to solve the problems. Increment and stabilization, if you want any stabilization. Next, the type that okay, that increment is how that incrementation will take place. For example, in the case of static analysis, it can go in once. Okay, but if you have some other problem, for example, if you are trying to solve a very intricate part which requires small time steps to resolve it, so you can change it. So for example, it's a good habit to change it from 0 to 1 to some smaller part, because see, already only for one it is the time period is only one. So try to reduce it a bit so that it will actually what the solver will try to do, it will run it in the steps. If initial increment size is 1, it will run in once and it will be over. Okay, so what I'm trying to do is I'm trying to reduce the total time size so that we can have some steps, and always try to increase this increment size to large, so that if more than one iteration is required to solve it, it can take that. Okay, if it is will be one, it will actually show the error that okay, your results are not converging. So always increase it. Okay. Okay. Now come to this part. This part was not in last time, it was not getting open. So this is the field output manager. So you can select it from here. You can select it from here. Yeah. So once you have it, actually this thing is coming. So let me show it to you again. So defaultly one field output will be created which will have all these options pre-selected. But for example, for this case, I don't want all these. So what are the options which are actually available in the field output? There are stresses. Basically, which stresses you are using in your simulation. For example, basic stresses, stress variance, one minus stresses, maximum stress or equivalent stress, transfer shear stress, or the so if you are guys from mechanical engineering, I think you must be knowing all these parts. Elastoviscous network or plastic network, or it really depends upon the type of model that you have. Okay, the various types of stresses will be generated. Similarly, these strains, you have total strain, viscous strains, plastic strain, equivalent viscous strains, inelastic strains. Number of types of strains are there as per the respective applications. Let's come to there are displacements. You can select the translation, rotation. We have velocities, translation, and rotational velocities, and acceleration. Forces and reaction tab is there where you guys can select all these things. If you have contact, you can get the contact stresses, contact displacements. If you want to store the energy, so all energy magnitudes you can select. If you have failure or damages, you can have the respective damages. So I think in the second session, when Sumat will be explaining you guys about the impact, I think he might be having one of these options open for you guys. For thermal case, you can have all these basic temperature options, then electrical and magnetic, and then pore. If you have a pores or void, you can select it. If you want to select the element volume, sometimes these are also very helpful. If you want to turn on the error indicator, you can do that. Let's see, here it is. If you are writing a subroutine, then in that case you have to on it. Okay, this solution dependent solution variable. Otherwise, what will happen? Even if you select written a subroutine and you haven't selected it, your output will not have those variables. Okay, even after running. So always select this option. This status option is also important for failure and plasticity model. So always remember this thing. And you can save the volume fraction. Okay, so for our current let's stop the introduction part. Now let's move to our problem. We are trying to deflect a beam, and that beam is one second. In that beam, what we want is we need the stresses and the displacement. That's it. We want these two things in the whole model. Okay, history out manager, these are also options which are available which you can store. So let's remove it. Okay, and we don't want any history output manager. Let's just turn off this option, because we don't want that the model should take more than what is required for us. Okay, so now once the step is decided, what you have decided, the output variable you have decided, we don't have any interaction in this case. Let's go to the load option. Now what two things we have to define. One is the loading, second is the boundary conditions. Okay, so what we have the point load in the end. Okay, just select on it. So here in the load module, what you have all various types of loading patterns. For example, you have concentrated force, you have moment, you have pressure, shell edge load, surface friction, pipe pressure, body force, gravity. So all this basic the Collier's force, the connector force. I mean, I think these are used in fluids. So all these basic forcing options are there. Okay, so click on concentrated force and click on. We want to define a concentrated force in there. So, and even electromagnetic and other things are there. So it will be totally defined as you are selecting your model. Okay, so we have a beam which is getting deflected in the end. So we'll select the concentrated force and click on continue. So once you will, now it will ask for select the point for the load. Okay, so once you select where we want to define it in the end. Okay, so just select this point and click on done. Now this box will be open. Now it is asking for the value of the load. Okay, so this 1 represents the direction 1, that means x, and 2 represents the direction y. So what we have to define is we have to give a load of, let's say, 2 Newton downwards. So it will be -2. Minus represents the downward direction. Okay, click on OK. It will have a load in the downward direction. Now we have defined the loading condition. Let's define the boundary condition. Now boundary condition manager, once you click on create, it will have all similar options which you have in loading, but it will have in the various domains that we had discussed before, that in electrical case and mechanical case. So what we have to define is the displacement. You have displacement, velocity, or the axis symmetric condition. So select displacement, rotation, and click on continue. Now once you select this point and click on done, it will open this box and ask you to define the respective the manual displacements which are 0. So as we are fixing it, all 3 of them are 0. Okay, click on OK. I hope you guys can see this. 2 this orange and 1 blue option is there. So these represent that okay, all your direction are constrained. Okay. So now after this, we have defined everything, all the things that okay, we have created the part, assigned the properties, created the assembly, and done the stepping, assigned the solver. Then we have defined the load. One thing which is left is the creating mesh. Okay, this is the meshing module. As previously it was not getting open, so we are not able to discuss. So from this we'll select the seed part. Actually, seed part instance is an option where you define the global element size in the model. Okay. Second option is the seed edges. Seed edges could be used to provide the respective seeds locally. So if you have a global, let's say in a case is there where in a plate I want to have more refinement in the middle, and at the edge there is not large deformation, so I want to have some coarse mesh over there. So in order to move from fine mesh to the coarse mesh to the fine mesh, you can use these options wisely to get to the respective mesh. Okay, so this is a mesh part instance. So using this you can mesh the part. This fourth option is the assign mesh control. Okay, so first thing which actually whenever I'm clicking this clicking any icon, it is telling me that dependent part instance cannot be edited or assigned in mesh attributes. Try to operate on the associated part. So initially in the part we decided that okay, we'll be meshing part by part. So currently here assembly is being selected. So just click on this part. See, now all the options will start working. Okay, so firstly what we have to define is the assign element type. Okay, just select the domain and click on done. So element type selection could be done from here. So it has a respective beam element. It has all those elements which you are expecting, that okay, it has a 3D element, 2D element, beam element, plane stress element, plane strain element. So 1D, 2D, 3D, all 3 types of elements are present in. But yeah, respective higher refinements are available. That is a question mark. So you have to see as per your problem and how you are trying to define. Okay. So currently we have a beam model. So beam element is available, and here you can have linear or quadratic element. Actually, if you have read the finite element course, the more higher order you will go, the easily you can get the convergence. Okay, so though it does not have the capability of having the element order more than quadratic. If you want to add it, you have to go it using subroutines and other things. Okay, click on OK. Now you have to select the region in which this element type has to be assigned. So I'm selecting this part and I'm clicking done. Okay, click on OK. Now click on done. Now we have to select the size of the element. Okay, so let's say it's a 1 meter beam. So I want to divide it into a 10 parts. So approximate global size 0.1. That much is sufficient. So all these 10 elements will be created. From here we are deciding the number of elements which will be created inside the model. Okay. Now once you have created that, click on this mesh part option. It is asking that okay, mesh the part. Once you have defined these options, it will ask that directly ask that okay, mesh the part, click on yes. So see, now color has suddenly changed and you have this new meshed part. Okay. Okay, and one more thing, in the message box also you can see that okay, 10 elements has been created in the beam. So new 10 elements has been created. So if you are not sure that okay, how many things has been created or whatever it is, so message box will sometimes will be very helpful. So I think we have done all the meshing modeling parts. So our pre-processing portion is almost over. What I'll do, I'll save this. Press Control S. Okay, now I have saved this model. Now let's go to that folder. Let's see what are the changes that has been happened in that file also. Okay, so I'll share it with you guys, this new screen. Okay, so number of parts which are present, they are almost same. The number of files which are, they are almost same. But this JNL file, let's open it. That how it has changed. Actually, this JNL file is the file which contains all the information. So I'll share it with you guys. This JNL file, yeah. Okay, so this beam.jnl file contains all the information, all the processes that you are trying to, that we have done till now. See, so these are the, see, initially only this first line was there. Now I have created all these things. So each and everything will be written here in this Python script. Okay, you have part import, material import, all these are basic calling options. Then sheet size, we initially we defined the sheet size in the Abaqus. Okay, when we decided to select the part, so 2.0 was the sheet size. Then we gave the coordinates, they are here, 0 and 0.1. Then after that we selected that okay, what are the next thing we did, is sketching option. Then we defined the elastic properties, they are here. Then we defined the part, once we did, then we decided the cross section. See, all these things are there. So these are actually are the inbuilt. It is in the inbuilt Abaqus script. Actually, it is a Python script which is created by the Abaqus. Okay, so everything that we have done till now is here. Then we say section assignment. We did section assignment. So section assignment is here. Then after that, we created the assembly. So assembly is there. Then we selected the history output request, field output request that is present. After that, we defined the concentrated force. So concentrated force is here. So all the basic options that we have given one by one has been listed here. Okay. So this is something important which I wanted to show. Okay, let's cross. Oh, sorry. Okay, so now let's get back to the model. Now we have created the mesh. Okay. Now, not we have, what we have to do once mesh is created, we just have to, we don't have to do optimization. We'll just go to this job module. We'll create a job, and once the job runs, we'll observe what are our results. Okay, let's create the job name is beam bending. This is model 1. Click on continue. Select OK. Let's go here. Okay, so we have created a job naming beam bending, and it has model 1 and the type of analysis and the status. So you can always do a data check. Okay, see, when I click on data check, it is asking me for that in the model region or the part of the beam have not been selected. So there is a thing which I haven't defined. So while you will perform the data check, it will show something. It will show the thing if you haven't defined it. Actually, because of this zoom option, I'm not able to see number of options. So okay, so let's go to the property and then assign. We have this beam section orientation. Actually, what has happened is that cross section direction I haven't given. So if you don't define the dimension of the cross section or the section that you have defined, it is not going to work. So once I select the assign beam selection orientation, it is asking me to select the region in which I want to assign the section. So let's just select this and click on done. So it is giving me the direction. Let's say okay. So now I have defined the beam orientation direction. Okay. Now let's again go to the job and try to give this data check. In the model, regions of the part beam do not have beam section. Sector 1. 1 second. Let me do it again for once. There's some error here. Okay. Now go to job status data check. Yeah, see. See now I have defined it again. So now when I'm clicking data check, so it is telling me that history output is not registered. So we have turned it off, right? So we said okay, yes. So now check has been submitted. Let's wait for a second. Check is running. And once we have submitted this check, actually this check will check all the data, all your input files, that okay, all this data that you have entered is okay or not, something is incorrect or not. So see, check is completed. Now you can submit your job. So just click on submit. Click OK. Again, it is asking that history output is not given. Yeah, we haven't given it. Yes. Now see, using this, we have submitted the job. So click on this monitor option. You can always monitor what how this job is running. Okay, so it has step, increment, and other things. One thing which I wanted to show is that initially the see our job is also completed because only 10 elements are there. It will run very fast. So what they're also 1D parts, so it will run very fast. So what I wanted to show is initially we reduce the time step from 1 to 0.01. Okay, if I had defined it in only one, if I haven't reduced it, so it would have only one single step. Okay, but now it has all these steps. And in the incrementation also, see, once this has incremented, the step size has been increased slowly. So this will be there once solver sees that okay, your time increment, the time increment which you have given is with that your results are converging, so it will try to increase your time step. Click on dismiss. Okay, now we can click on results to go to the visualization module. Actually, this is the basic visualization module where you can see your output. Okay, so this is the basic structure. Now these are the various options which you can turn on. So click on this plot contours. So it is showing you that okay, your beam has gotten deformed, and from here are the basic options. One second. Actually, this zoom icon is see here you have on the top right hand side you have this option to select the displacement stress. We have defined only three things. Okay, displacement and stresses. So in the stresses you can select S11. Okay, so initially we have to check the displacements. Okay, that what are the displacement values that we have obtained. So let's go to U1 and U2, two directions are there. Select on U2 along the y direction, how much is the displacement. So the value of maximum displacement that we are getting is close to 7.375 E minus 8. Okay, so let me show you using some options here. if you select this in the contour, if you'll keep on holding it, you will have this option of showing both, means the deformed and undeformed shape. So click on it. I hope you guys can see both the undeformed, the deformed shape. Actually, this value is very less. So what Abaqus is doing is it's showing it largely. So don't get confused with that. Okay, this is a very small deformation which we have obtained. I hope you guys can observe that. Okay, this is 1 meter and this is 7.35 e minus 8. So this is a very small value, but it is trying to show it by amplifying the image. Okay. So now let's go to our presentation back. Go back to the present and let's check the stress. So as you guys can see, the maximum stress S11 we are getting here, where the beam is fixed. Obviously, we'll get the maximum stress there. Okay, and its value is close to 1.42 e minus e3. Okay, so it is 1425 Pascal. Okay, so let's go back to our presentation and see, analyze what we have got and what are the standard results for this case. Okay, so let me share the screen again. Okay, so this was our problem. Yes. Actually, I'm using this Zoom for the first time, so again and again I have to switch it from here to there. Okay. Yeah, so this was our problem. So what results we have gotten? Okay, so we all know that, okay, the basic quantities that are available, the end load formula is, the direct formula is there, everyone read it out, that it is WL cube by 3A. Okay, its analytical value is this, and with Abaqus we have, with the coarse mesh, I mean, for this is a very coarse mesh, right? We have taken 10 elements only, so we have gotten this value, and the maximum stress, it has PL, means moment, means My by I. Okay, it is straight, so this moment is PL at the end, Y by I is the moment of inertia. Okay, so its analytical value is 1500. Okay, so what we have gotten is this. So one thing which I wanted to show is that, show you that, okay, the results which we are getting, they are close to the standard one. Okay, and when you will refine it, you'll check your model, you'll do things, so you can always get the, you can always reduce the differences, and there will be some difference, because in the end analytical values are like, if you're trying to fit a curve with a Taylor series expansion of the higher and higher order. So in the end, we are trying to make the approximation. We are making a compromise. So that compromise will affect you here. Okay. So more the accurate your modeling is, more the better the results you will get. And one more thing is that this stress value is a post-process quantity. It will always have uh, some more difference, because um, some more difference, because it will add on well while you post-process it. So number of times it is there that, okay, your error will be propagated from your lower variable, means the basic variable, to the post-process variable. The displacements which you have obtained, they are the direct one, but the stress you calculated from the displacement, so it is the post-process quantity. So it can lead to the increase in the result. Error can get propagated from your basic quantities to the post-process quantity, so it has to be, yeah, so you have to consider it if you are trying to solve. Okay, now let's move to our next example. Saurabh, can I take 5 minutes break here?
Yes, yes, please, sir.
Yeah, so we'll take a 5 minutes break, then I'll continue. Okay.
Yeah.
Hello.
Yes.
Hello, Saurabh. Okay, so I'm starting it again. So welcome back. So let's move to our second problem. This was a 1D representation. Okay, how you can solve a 1D problem, and we have tried to see that okay, the results which we are getting, they're almost close to what we have seen in our past. Okay, so using a finite element, what we are trying to do, we are trying to approximate our solution, okay, using different elements. So now let's move to a 3D problem where I'm trying to explain you guys that how to do a model analysis. Okay. So what our aim is to calculate the basic natural frequencies of the system, and I'll be explaining it using 3D elements. Okay. Okay. So let me share the screen again. Okay. So we have done it. So let's just save it and click on new file. Let me change the directory first. So from that we have, let's it's a plate. Okay, plate model. Now I'll change this work directory again, move it to a plate model. I'll save it with the name plate. Okay, so again we are going to follow the same procedure. We'll start with the part. Everyone, Saurabh, are you able to hear me, right?
Yes. Yes.
Okay, so we'll select the part. Let's name it as plate. We have a 3D part and click on solid. So this is the approximate size of the screen. Actually, last time I forgot to explain you guys. This is the approximate size of the sketch screen, which will be coming after I click on continue. Okay. So let's for this case we have a very small plate. So we can have any random plate. Okay. So let's define it as 10. Click on continue. Define the size of the plate. So first point is 0. It's a rectangular plate, so I'll just click on 1. So let's plate is 1,1. Okay, click on enter. So it's a square plate. 1,1 plate. Depth, let's say it has depth of 0.2. Click on. So this is the same extrusion option. Okay, that it will get extruded about this face. So click on OK. Now our plate is created. Now select the property. And now we'll assign the properties again. Let's again say we have steel this time. Now in this case, as we have to do the modal analysis, so we have to define the density, because in the end natural frequencies will be dependent upon, we have to whatever in order to calculate the natural frequencies, we'll be needing that mass matrix. Okay, so for that mass matrix we have to define the mass density. So let's say density, if I remember it correctly, it is close to 18,100, and mechanical elastic. Okay, so young modulus of steel is close to 210 E9, and Poisson's ratio is 0.2. Okay, click on OK. Now once we have defined the material properties, we have to create the section. Now in this case we'll create a solid, we'll create solid 3D elements. Okay. Click on continue. It's a steel, so click on OK. Now we have created the section. Now see, in the last case we have to define the parallel cross section, right? We had defined the that one part initially, 1D part, and then we created the section. But in this case it's a 3D part, so you don't have to create that separate section again. So in this what I mean to say is we don't have to create that perpendicular profile in this case. For 1D case, you have to define the cross section. For 2D case, you have to define the thickness. And for the 3D case, you don't have to define, because all the dimensions are fixed. Okay. So click on assign section. Select the part. Click on done. Now it is asking for edit section assignment. So click on OK. So as you can see, once you will assign this section, its color will be changed. That means the properties has been defined. Now go to assembly. click on this. Now again, we'll select the dependent part. Go to step. Now here there is something which is going to be changed. Now what we are interested in doing is we want to calculate the natural frequency. So just go to this linear perturbation tab. Actually, this is similar to the why there is it is a separate tab where a small perturbation is taken and all those values are set. So if you want to explore it more, you can just go to the manual and you can see it. Okay, so it's a go to the linear perturbation tab, select the frequency, click on OK, continue. Sorry. Now it has the various now how the natural frequencies are actually calculated. If you guys know, you have to calculate natural frequencies are calculated using an eigenvalue problem. So in the Abaqus, we have this Lenzos eigenvalue solver, subspace eigenvalue solver, and EMS eigenvalue solver. But this Lenzos eigenvalue solver is the most general one. MATLAB also has it. So if you guys use MATLAB, you can always check these results parallelly by writing a small code. Okay. So this Lenzos eigenvalue solver. Now number of eigenfrequencies you have requested. So if you will click on all, so all eigenvalues will be listed. So let's say currently we are interested in let's say initial 30 eigenvalues. Okay. And now and the maximum you always define the maximum up to, let's say, up to 5,000 hertz. I want the my natural frequencies, because what we are always interested in are the minimum 5 to 10 eigenvalues, because they are quite dominant in the nature in the dynamic response. Okay, so let's define our maximum frequency of interest as 4,000. Let's say it's a random value I've taken, so you can take it as per your analysis. Okay, so click on OK. So once we have defined it, just go here, field output. So only displacement has been selected, that is okay, and no ST output variables. Okay, so in the load, so in this case, let's say it's a free plate. Okay, it is just making the natural oscillations. It is doing only the natural vibration. No forces involved, no constraint is applied. Okay. This next problem, I'll try to constrain it and let's see that, okay, what will be the effect on my natural frequencies. Okay. So it's a free plate. It is just getting oscillated under the environment. Okay. So just go to mesh. Now here, again, the same error will come. So just select the part. Now click on this S4R. So we have to define the element type. Okay. Here. So we can define it will run in both of them. So we define standard linear. So see the family family of element which is it has it C 3D stress. Okay. So in this sorry, in Abaqus, the various types of element which you are using will be listed here. Okay, and these are the various options which you can use. I didn't explain it in the last section because 1D element was very simple. Okay, so in the 3D element, what you can do, you have all this formulation. For example, for hexagonal case, you can use hybrid formulation, reduced integration. Let's unclick it. Okay, with actually reduced integration is helpful when in the large deformation problems where if you are having certain issues with your options. So see this R glass control will be removed once you untake this reduce integration problem. So when your actually problem gets stuck, in those conditions, these options are really helpful. Okay, for example, in contact problem, high deformation cases. So in those cases, actually, this option will be very, very helpful. Element deletion can be there. Okay, if you want to, if you have an element which is getting highly deformed. So after how much that, let's say I define some value that, okay, after 20% of deformation, it has to be get deleted. So using these techniques, actually we define the failure models. Okay, so you can always define the maximum degradation. So I'm talking about the failure cases. Okay, yeah. So for the R case, basic structural analysis has to be done. No large deformation cases. So these are the basic. So options element which we are using a 3D C3D8 is a here 3 defines the dimension. Okay, that it's a third dimensional element. C defines is cubic, and 8 defines the 8 node brick element. Okay, so click on OK. Now we have defined the element type. Okay, now let's give the global seeds. This is 1, so let's reduce it a bit. Let's give it 0.01. See, it's a fine mesh this time what we have selected, and click on this. Okay, mesh. See, now we have created the mesh as okay. Now once mesh is created, just click on create, go to the job tab, and now click on continue. Just try to perform the data check. Okay, sometimes data check, although you even if you omit the data check, but it is always a good habit to check your data initially, then submit the job, because with that all your files will be created inside it. Let me show you that. Okay, all these files are getting created. See, once I perform the data check with the job name 1, all these files are created. So let me show you that folder. Okay, plate model. Okay, see, all these files with the job names are created after I submitted the data check. Now what you guys can do means, one number of times what we want is we use command panel to submit the job. Okay, so in that only this input file, one INP file will be created. Once this input file, and I think the CAE file, these 2-3 files are there which are very much important. Using that you can submit the job directly. So let's share it. So as we have taken a large number of elements, it is taking large amount of it, large time to check the run. So what I'll do, I'll reduce the number of elements. I'm killing it. And I'll do, I think it's taking time to get killed also, because I'm running it on my laptop now, so it's taking time. So go to mesh again. What I'll do, I'll change the global mesh. I'll reduce the number of elements. Let's say it's 0.05. You're asking for delete mesh. Okay, delete. Okay, and I'll remesh it. Okay. See here one error was also, it was showing one error that okay, your memory allocation for the job was increased to 1792 MB. So actually it depends upon your system that you are using, right? That how much power does it has, how much memory size it has. Although it was completed, so let's resubmit the data check. Okay. This time I don't think it should take much time. You can always monitor it. Okay, from here you can monitor it. So slowly it will show that okay, everything is completed. Now all those files will be created at the back. Just submit the job and monitor it. So what you are seeing is once that those all options are done, once data check is fine, so what you guys can do is just submit the job and leave it. Okay, so in the last set of analysis, what we guys do always do that. Okay, just leave it in once. See, in this case I haven't changed that step size, so in the single step only it is completed. Okay, so actually we are interested in only natural frequencies, so time stepping won't be actually much thing to change it. So yeah, this is the basic change, basic what it is showing. So now we have to see that what are the natural frequencies that we have observed. Okay, so let's go to the step option, go to results and click on this step and frame. See, here are the list of all the frequencies that we have selected, and I think I gave a maximum frequency of 4000. So above that, no single value has been shown, and initially actually it will give some random values. These 5-6 are the garbage values which Abaqus actually gives because of the numerical error. So always try to see that okay, so there will be some dominant value. That you see, natural frequency can't be 0. Okay, and that means your stiffness is 0. if you see, this is like that only. So natural frequency is a square root of k by m. So it can be zero only when a stiffness is zero and the material which you are using does not have that zero value. Okay, so you, whenever you are trying to perform the simulation, always cross check your result that okay, the value which you are getting is it in the domain that you are asking it for. Okay, have some basic estimate. For example, in the last problem I showed you some benchmarking, okay, that the value should be close to this for some benchmark problem, and you can forward it after taking that reference. Okay, so always try to solve some benchmark problems with some known results so that you can have some basic estimate that okay, my analysis is going in the right direction. Okay, so the initial the minimum frequency that we have obtained is close to 575. Okay, this is a free vibration case. If you want to plot it, so what you guys can do, see these are the respective mode shape. If you guys can see, they actually have made a sort of thick plate, so you guys might not be able to see. So when I'm changing it, no, see this, these are the respective mode shapes of the plate. I hope you guys can see it. They look really beautiful. Yeah, so okay, so what I will do, will try to make some changes in this plate and see that okay, how this minimum frequency's value is changing from 575 to some other value. Okay, so let's go to load again. What I will do, I will constrain it. Okay, constrain its edges. Continue. If you want to select more than one face, you just have to click on shift and click this. Okay, and if you want to rotate it, press Control Alt, then you are able to rotate it like this. Actually these two keys are very much helpful. Okay, if you are doing with me, you would have seen that. So click on shift and select this. Okay, so you'll be able to select multiple things at a single time. Okay, and click on tab. Now I'll fix all these things. Okay, all degrees of freedom, let's say they are fixed. Now again I will run the job. Let's say it's a job 2 for model 1 is fixed. Okay, so now click on submit. Select submit it directly. Okay, this time. We know there won't be any error because everything I have checked. So it's a very simple problem, but so I've just submitted it directly. Yeah, it's complete. So click on dismiss, go to results, and click on contours. Yeah, it is getting deformed. Now go to results and go to steps. See, its minimum value has been increased. Okay, frequency. So obviously it is increased from 575 to 1321. Why is it so? Because we have increased the rigidity of the structure. In the end, we have tried to do we are trying to get the frequency of a more rigid structure, so the stiffness matrix will get enhanced. Okay, so in that case, in this case the natural frequency should get increased. Okay, so it is getting a higher value. Okay, that's what I wanted to show. Now let's move to up. So okay, now I think you would have understood the basics of that basic terms, that okay, these are the basic what you say, the basic steps which we follow to get our finite element results. Okay, using Abaqus. So now I wanted to show you one example where your basic this cuboid element will not means this brick element will not be able to mesh it. So let me explain you one more example which is very interesting, which is having a cube with a hole. Okay, cube with a hole inside. So let's select let's go to and change the directory to the new one. Okay, and save it to the same file. Define cube, model name as cube. Okay, So what I'll be creating, what I want is, I want to create a cube and a hole is inside, a spherical hole is inside it. Okay, so how you model it inside Abaqus? Okay, and when you will try to mesh it, you won't be able to do it with this brick elements. So I'll show you that how you can easily mesh it. Okay, so continue. Now select, let the edges of the cube are 1 1 1. Okay, then done, and its depth is also 1, so it's a cube. Then what I have to do, I have to, in the end, how you have to actually do it in a number of ways. What you can do, you can create a separate spherical part, you can merge it and create while merging you can cut it. Okay, what other thing you can do, you can just create a section at the center and create a semicircle and perform a revolve cut. So number of ways are there by which you can do that. So I'll be doing it with the help of the section thing. Okay, so we have to create a datum plane because I can't just sketch it in the middle. Okay, so just click on this create datum plane, and which plane we want to make is a XY plane. Okay, so create on XY plane, and it is asking for offset. So how much offset we have to go? Let's say 0.5. And see, this offset plane is created. So now what I have to do, I have to create a profile on this plane and I have to revolve cut it inside so that there will be a hole. So it could be considered as a damage inside a structure. Okay, there is a small damage inside a structure. So what you can do, this is an option of revolve cut. Actually inside it number of options are there. Extrude cut also, cut revolve, sweep cut, loft, or circular hole. So actually these all options are all are present in the general purpose software. So it is almost similar. So just click on this revolve cut, and it is asking for a plane on which you want to perform it, and it is asking for the edge that will appeared while we are drawing it. So okay, so let's consider this edge. So it will come here. It will come take us to the sketch tab. So in order to make it, let's create a circle first. So I'll select it. Let that tab has the dimension of 0.1. Okay, so it has a so I think I did it very fast. I'll trim it again and do it again for you guys. So what I have done is it is asking for the center. So I have selected origin as the center. Second thing which it asks is pick a perimeter point on the circle. Means on the circle any point you create, select, it will be done. So what I have typed is it has a perimeter point of 0.1, 0. So that means it has a radius of 0.2. Oh, sorry, 0.1 radius, and okay, so that's how it is. So now we have made the circle. Now when I will click on done, it will ask us to create a construction line, because when we are doing a revolve cut, it need a line about which it has to get revolved. Okay, so click on this. There are ways to create the construction line. So I think a construction line option is directly here. Yeah. So create construction line, and you can select one point, and we have to select the end point. So see, this vertical construction line is created, and then what we have to do, we can trim the other part. Okay, so it will get revolved about this, and we just have to close it. One second, guys. So click on done. Now it is asking for the angle. It is asking for the angle, that how much rotation it has to take. So it is 360. Okay, so we have created a spherical hole inside a cube in this case. now I'll show you that although it is created, but we can't see it because it's inside, right? So go to these viewing options. This tab actually has the basic viewing options. So once you will, these are basic X, Y, Y, Z, and this is the isometric view. And here we have the basic options. So when you click on this wireframe option, yeah, I hope you guys can see that we have created a spherical void inside it. Okay. Now this option actually it can show you the cutted view. So once you will click on it, you guys can see that okay, this cutted sphere has been made. Okay. So one more thing is, so okay, now we have created the part. Now let's try to mesh it. Okay. So I'll do the same thing, 3D stress. Okay. And I'll try to make a mesh with so 3D stress element that we had taken in the last part, same we have taken, and 3D C3D8 elements, and let's try to mesh it. Click on OK. It has taken the global sheets. Now see, the selected region cannot be meshed automatically using selected elements. So see, this is how you have to see things. That if there is a void, there is circular structure, that a respective element type will not be able to help you in that. Okay, for example, cube cannot be used or will not help you in a spherical void case, because it will not try to interpolate near the surface of the sphere. So just click on the so what we have to do, we have to select some other element, right? So go to this assign mesh control option. Here you can change the mesh type. So select this tetrahedron option, okay, and click on OK. See, the color has changed. So it is very good with Abaqus that okay, if you are doing something different, it will try to show you with some other color so that you can see that okay, I have applied it. That you will get confirmed that okay, things have been applied to the structure. Okay, now go to global sheets and try to mesh it again. See, your structure is meshed now. See this. I hope you guys can see that okay, inside this void also. See this, they are nicely interpolated. So you always have to see that in finite element that okay, one respective element type will be helpful for you guys for the respective uh, for a respective case. Okay, and the other thing is that how for example, in my case, I have been developing my finite element code since very long. So in my case, what I have seen is once you change the type of model or the type of element you are used, your results will change drastically. So always try different elements. Let's see that okay, with this element I'm able to get the best results. It is try to interpolate my model in the best way. So always try to see these things. Okay, now I think I have 10 more minutes, so I'll try to give you one more example about meshing, which I already explained to you guys that okay, how this sectioning is helpful to you guys while you mesh it. Okay, so I'll create a new file. Okay, I'll create a new folder. New mesh, and I'll change the directory. Okay, so okay, I have changed the type and saved it as a new model. Now let's mesh a part. Now let's mesh a plate with a circular hole. Okay, I'll try to show you that how auto meshing or the free meshing can leads to you creating various errors. Okay, so let's have a 2D planar model with a shell. And click on continue. Now let's create a rectangular plate of 2,2. Okay, and done. And create a circular hole in the center. So it will be close to 2.5, 2.5 and 0.5. So 2.5, comma 3. Oh, sorry. I think I did it the wrong side. What I'll do, I'll shift the center. 1 second. I'll do straight. I'll try to create this rectangle again. Okay. So select rectangle, click on -1, -1. -1 is the starting point, and 1, 1 is the second point. And I have created a hole of 0.5, 0.2, comma 0. Yeah. So this is a plate and it is having a hole. Okay. So click on done. So now let's try to mesh this thing. Okay. Go to mesh and see, I have already explained you guys about 1D and 1D elements. So for 1D, it has beam and truss elements, okay, which Abaqus has. For 2D, it has plane strain and plane stress elements. These are the two general elements which are and quad and triangular. And these two types of analysis types is there which you can select. And these basic options I have already explained to you. So we are considering plane stress 2D elements. Okay, click on OK. Now seed part. Okay, so let's do it using 12.01. Click on OK. So it's a very fine mesh. You guys won't be able to see it. So 5 minutes. And now I'm auto meshing it. See. So in this kit, what I hope you guys can see that, see, although I have selected a quadratic elements, number of elements are very close to triangle. So what will happen when you will try to elongate it? What will happen? These elements can lead to the distortion error, because when a quadratic element under deformation leads to have some certain angle, more than some certain angle, it will start showing the deformation error. So what you guys have to see is your quality of mesh. Okay, your quality of mesh has to be optimum in your FEM analysis, otherwise you can lead to number of errors. Okay, so how to remove all this? So this thing, see, this is only a particular case, it is not generalized, but okay, with the use of sectioning, actually you guys can remove these things. You can mesh it using structural meshes also. So what we have to create these sections. So here there is a option called as partition sketch, face sketch. So some regions will be individually meshes will be individual by partition. So select it, partition cell. It was here. Okay. See, so once you select the partitions, one second. I haven't deleted the mesh. I think that is why these options are coming. So do one thing, just delete. Once you will hold this tab of mesh, it will have this option of delete part. So I think I made some error here. Yeah, so now all the data related to mesh has been deleted. I already deleted the mesh. Now go to part again. We have to sketch. See, now once you select it, once you select this partition sketch option, it will take you to the sketch part, because only in 2D only once one face is there. If it's a 3D, it will ask you that okay, on which face you want to create the partition sketch. Okay, so we have selected it. Now go to this. What we will do, we'll try to create partition about these 4 points. Okay, what we are trying to do, we are trying to distribute it in the 4 parts, but nodal connectivity will remain the same. Okay, so you don't have to worry about it. So just try, in order to make the model, we are trying to partition it, and all the connectivities will remain the same. So it's a very nice option in Abaqus. So I hope you guys can see this. Now we can select different parts separately. Now let's go to the mesh part. And okay, so go to this thing, the assign mesh control, and select this part. So initially it was showing only free option. Okay, now that structure option is on after I partitioned it. So whenever you click on structured option, click on OK. See, now we can assign the structural mesh. So now let me try to mesh it again for you guys. Let's say the mesh size is same 0.1. Okay, click on OK and try to mesh it. I hope you guys can see that. Okay, although it has some elements which need to be taken care of, but almost all the parts, all the elements have at least quadratic nature. If you will try to refine it more, you can get the better results. So like this, you can always check your mesh and get the better output. And if you are having the distortion problem or any other problem, you have to check your step size and your mesh, okay, accordingly. So, and the more better your mesh is, the more better results you will get. So, okay, Saurabh, this was the last example. I'm done from my part. So we can have the questions now if you have collected it.
Yes. Sanjay,
Hello?
there is one. Sanjay. Yes, thank you.
One second. Let me connect to my headphone. Okay. So your voice is not that audible, just coming very slowly. So one second.
Hello. Hello, Sanjay.
Hello, one second. I'm able to hear you, but I'm just trying to connect it to my headphones. Okay. Yeah. Hello.
Yes, Sanjay. Yes. Sanjay, can you?
One second. The headphones. Yeah. Hello.
Yes. Okay.
Yes. Yeah. Okay. Now it's. So
Sanjay, can you show immediately how the output data will be used for some other codings? Then you go for the further questions.
Output data.
Yeah.
Means you want to see the output data, that how I can use, how we can save the output data. That's what you want to ask.
Yes.
Okay. That's the sure thing. So let's open one of the analysis that we have done. So we have performed the beam analysis. So click on it. So save changes. Okay, it's fine. So we have performed this analysis. Now we have to change the work directly to the one which we had selected previously. So beam one. Sorry. So beam one is okay. Okay. So beam. We had already got all these results. Okay. Now let's say I want to save this data. Okay. So there are a number of ways actually. Let's say firstly I want to save this file, save this plot. Okay. So what you can do is you can just can print it directly. In the print you have number of options. Printer can be you can directly give it to a printer, or you can do the page setup also. There are number of ways or options are there to export your data. So and if you can even print it to some file. So see, JPG file is there, SVG, TIFF and EPS, all these standard image formats are there. You can, if you want to save it in the PDF, just print it, and if you want to save it in a respective file, means for example respective image, you can do that. So let's say beam, click on OK. See, the specified viewport is been printed to file beam.png, and now when you will go to that beam folder, see, share, put back. In this beam folder, I have selected beam.png. So it's already saved, right? Yeah. So one more thing which I forgot to share with you guys, that okay, you can save all this data to some, let's say I want this data actually. So what you guys can do, click on this XY data and select this history output or field output. So click on continue. From this, you can save data directly. So for example, I need only data. I don't need the image. So go to the centroid or element. Let's say I want to save this stress initially. I need S11. So from here, you can plot also. And if you want to save it to all, so select, you can select it by respective element or by all. So just save, this will be saved in the file where it will be saved is from here. 1 second. Click on save and click OK. At least one selected entity. So sorry, you have to select the elements. Okay. So you can just I think internet connection is lost. Hello?
Hey, Sanjay, can you share your screen?
Yeah, sorry. I think some internet interruption happened. Okay.
Yeah, yes.
So I'm there. Okay. So now here it is. So once you can slightly save it in some file. Sorry, in report. Sorry. Once you save it from here, then just go to report and click on this XY. So see, all these things that we have selected is came here. Go to setup, and the name is here, that abaqus.rpt. So in this file, your respective data will be saved. Okay. So XY data, click on OK. At least one data has to be. So let's click on all this data. Let's click one data. Okay. Click on OK. So see, XY report has been appended to file abaqus.rpt. That means your data has been saved there. So one way was I showed you how to save a contour plots. Now let me show you that what has been saved over there. So let me share this screen again to that file. See, this abaqus.rpt file has been saved here. Using Notepad++ or any Solo, you can save it. Okay. Now for all the elements, sigma xx has been saved. Okay, I hope so, Saurabh, this was able to answer your question.
Yeah.
Please continue.
Sanjay, can you open this chat box for the further questions?
Okay, one second.
Yeah.
Let me open it once. So, chat box. Actually, I'm doing it for the first time, so I don't know much. 1 second. More chat. So, how to share it? Actually, I don't know. So, is it visible now for you guys?
No, I open actually. So I read the questions and you just give these answers to
okay. Okay, I'll give it to you. So I'll start it from the first, sir. Your voice and Abaqus is a software. Okay, that is fine. What is the difference between explicit, standard and explicit solver? That is the first question from Anshul Agrawal. So as I've already explained to you initially, that see, standard is a general purpose implicit solver. Okay, whereas the standard is a general purpose solver usually used for the low speed or the very small deformation cases. When you have to resolve the dynamics. So in that cases, your wave speed or the wave propagation in the structure is included. So in that case, actually the explicit solver is handy. So that is, I think, the basic difference. So what is parallelization? When this is the second question from Roshan Kumar. Sorry. So the parallelization, what I mean to say, you can use more than a number of cores in your system. For example, if in case you have workstation, you can use more than 2 number of cores in your analysis. Okay. The next question is from Vipin Chandra. Simulation time can be saved using parallelization. Yeah, oh sorry, he has actually answered it. So next question is how to change unit from mm to meter. So 1 second, I'll show you. I already showed you in my presentation, but if you are listening, you can just check it. I'll share the screen with you. You can actually save this. I hope you all guys are able to see that. See, this first one is in the SI system and second one is in the MM the SI, but in the MM. So in MM, actually, you have to convert it from kg to ton and Pascal to megapascal, joule to millijoule, or density from kg per meter cube to ton per meter cube. So like this, you have to change. Okay. Next question is from, you don't, sorry, how to give load stepping for fatigue. Okay, so fatigue is actually a dynamic problem where, okay, so load stepping you're talking about. So it's a general question, but I can show you somewhere, but in the end I also have to perform the simulation. So when you'll go for step, fatigue will be, I think, a dynamic.
Sanjay, can you please share your screen? Please
Okay,
share.
okay, sorry. Actually, I'm new to this now. So again and again I forget it. So okay, so this is it. So fatigue will be a dynamic case. So one thing what you can do is in the loading. In the loading, you can define a time dependent load. That thing you can do from here. Even for, I think, if you are performing a fatigue load, you can enter, if you are performing an experiment, you can give the tabular data, or you can create a periodic structure, periodic amplitude, and you can define the according that fatigue load that you are trying to do. And for the next, actually, if you need more help, I have to explore it more and get back to you. If you want it more, then you can mail, you can drop me a mail, and I'll be able to help you, I think, with this. So this is the one of the basic way that, okay, if you have a time dependent load, you just have to create the time dependent profile and apply that to the structure. Okay. So okay, can you solve a geometrically nonlinear problems like total Lagrangian or updated Lagrangian? See, updated Lagrangian or total Lagrangian. What I tried to show is was the total Lagrangian formulation only. But what for updated Lagrangian, I don't think. Abaqus. Actually, I have to see the formulation, how you are trying to formulate a problem. So, and for large deformation case also, actually, it was a very basic 2-hour time for me, so it was not possible me to cover everything. In large deformation case actually requires a lot of expertise and understanding of the basic concepts and the constitutive equation, how it is getting changed. For large deformation case, how you are considering the stress strain behavior, and number of things are actually is not inbuilt also. So you have to use the UMAT or VUMAT to add those respective models inside it. So actually, I'm also not that expert in it. I know the basics, but I haven't applied it till now. So I don't think I'll be able to help you much in this case. But yeah, you can apply. You can apply all these things in this. What is the next thing? Can we attach some plate? Sorry, the question is from Sudhir Vakle. Can you attach the some plate on another surface after stretching it? Can we attach this? What I can understand from his question is, after deformation, he wants to attach it to some respective place. Okay, so I think Sudhir, in this case, for example, let's say in my problem, in an impact problem, what happens is, if there is a impactor, if it supports the plasticity, it will get attached to it number of times. So yeah, it depends upon the basic physics of a problem. Yeah, we can attach it actually. The next question, go to file. Oh, sorry. Sir, can you please show the material assignment position in JNL file? So material assignment position. Okay, so I can show you that very easily. Now, 1 second, let me take you to that folder again. 1 second. And the JNL file, I'll try to edit and I'll share you with this thing. Okay, so I think material assignment. See, this is the section assignment thing which we assigned this section. Firstly, we created the, see, here we defined the material properties. Then we see aluminum we defined, then we created this section. Then we assigned this section. See, section assignment is here. So all these things are there. See, this is a Python script. If you want to use it, if you want to, you can make it, sorry, you can easily make changes in it if you want. If you want to, let's say, change the elastic modulus only, just change it and run it using that run script portion, it will run it for you. Okay, so you don't have to do things again and again. Okay, now Abaqus have an option of non-conformal meshes. Okay, so non-conformal elements, actually you have to understand for that. I don't think I haven't checked actually. Actually non-conformal meshes is actually used for the cases of the large deformation and other cases. So I don't think I have that test. I'm trying to do it, but still I haven't reached that point. So conformal meshes, non-conformal meshes, I haven't checked it. So I'm not confident of that. Okay, how to collect the result data from the desired node. So I think I have told you this thing. From Ramesh J asked this. And can I edit JNL file? Yeah, you can edit JNL file. As I have already explained it to you. You can edit JNL file. And which type of element used in beam analysis? Yeah, so beam analysis using Euler-Bernoulli beam theory is inbuilt in Abaqus. So what, how much, which type of element? So I think basic Hermite C1 continuous shape function would have been using. So in JNL file, can we see what we have done in material? Yeah, I have already shown it to you there, guys. Okay, so can we? So I think I have covered all the questions, Saurav. Yeah, so I think these are the all questions which student has asked.
There is one question is remaining from Dhananjay Yadav.
Okay.
How can we import dream3d.inp file in Abaqus? As I cannot see the microstructure in Abaqus interface.
Okay. 1 second. So what I'll do, I'll show you how to import the INP file. Okay, directly. So okay, so let's go to that folder. Our all analysis that we have done has an INP file. So it will be analogous. Okay, for all the cases. So here I had an INP file. See, this beam bending.inp is an INP file. What I'll do, I'll copy it and save it to this new folder. INP. And save it. And now what I will do, I'll try to import it inside the Abaqus. So let's copy its path. Click on set work directory. Change the working directory. Click on new. Okay, so you just go to file, import. Oh, sorry. Sorry, I always forget it. Okay, so share. And I hope you guys are able to see. So I have just changed the work directory to this new folder. Click on OK. Then go to this import and click on model. From here you can change it to INP. Okay, and just give the path. See, in this folder we saved that file. Click on INP, click on OK, and wait. It will be able to import your file. Okay, and it has all the options that you had created. Okay, all the data. Actually, I'll do one thing. I'll open INP file for you guys. Okay, so I think 1 second. Let me open that INP file using Notepad++. Actually, you can open it. So let me share this screen again. So see this. This is the INP file. Actually, it has all the data, basic data. So, for example, we defined the name beam and the nodes, node locations, element type, and then connectivity, So actually what number of guys does that they will try to create the mesh using Abaqus. They will take this data and they will perform some simulation. In their code, they will use these connectivity and nodal coordinate data in their code. So this thing could also be done. Okay. So I think Saurabh, this was able to answer your question.
Yes, yes, thank you.
Anything else?
Hello, Saurabh.
Yes, Sharad, please.
One question has been left, if you can allow me. Here.
Please ask.
By Ravinder Singh Chahar, can we give different material to different parts in the model?
Yeah, that thing I can show it to you very easily. So let me share. Okay. So let me share the Abaqus screen again. Okay. So let's create a part which has two sections. Okay, let's define a 3D part, or let's say 2D also, it's fine. Continue it, and let's create a rectangle. Inside a rectangle, what I'll do, I'll divide it into two parts. For example, I think heat conduction problems. Okay, two plates are connected in parallel. So what you can do is just go to sketch and try to divide it into two parts. Click on done. So now it has two parts. So let's say one part I want to define it as aluminum properties. Let's go to aluminum 79 0.3. Click on OK. And the other part I want to define steel properties. Elastic 0.29. Okay. So here in the manager, you can see we have created two parts. Okay. So here you have to select two sections also. So click on homogeneous. So we have defined shell. Shell. So click on this. Just define thickness as 0.1. Click on OK. Oh, missing values. Sorry, material. Let's say here it will ask for the material. So let's select first material as aluminum and create one more section similarly with thickness 0.1 and with steel. So when you will try to assign this section, now we have to assign this section. So select one part and click on done. So it will ask for, sorry, I think I made it. 1 second, please. I made some error. Okay, so does it not supported this type of section? Okay, so let's move to some solid sections only. Just try to select the material, plane stress. Yeah, plane stress. It's a 2D problem, right? So we have to select the plane stress with thickness 0.1. Click on OK. And create another section. Let's say for steel. And steel with thickness 0.1. So when you will have to go to assign section, select it. Yeah, it will ask for two sections. No, sorry, I forgot to rename it. The first section is for the aluminum case. Yeah, so it will change to aluminum, and while click on second one, click on done. So second one you can give on steel. So you can, I think from this tab you can see the different material. See, click on material. See, it has two materials. Hopefully it was able to solve your query, Sharad.
Yeah.
Hello?
I think, Ravinder Singh might have.
Okay, sorry. Okay, sorry. It's okay. So, Saurabh, any more question you want to ask?
Yes, I think all questions you cover, Sanjay.
Okay, thank
questions there. There is one question last. What type of the mesh is good for the aerofoils?
Aerofoils. Aerofoil is a
Tetrahedral.
Okay. So I think aerofoil has mode of spherical structure. Means what? How can I define it? it has a very smooth sections it has. So I think tetrahedron mesh should be better for the outer case. So inside what you can do inside, you can even use that cubical mesh, but at the outer face, tetrahedron mesh would be better, I would say. As far as I can see, I think I have shown you guys in that spherical. Oh, sorry, that spherical void example, that okay, tetrahedron mesh was better for the airfoil. Oh, sorry, for smooth sections, actually tetrahedron mesh is better as compared to hexahedron. Yeah. So next question is, can we perform different material models like part in one linear elastic and the part two elastic plasticity? Yeah, we can do that. Just you don't have to define this in similar way. I can show it to you. Go to edit, and here you can define the plastic properties. You can define that here, and the similar assignment in process will take place. See, you just have to be consistent with your material model. Okay, these things you can do it very easy. I think, Saurabh, we are out of the questions, so should we end it?
Yes, sir. Sanjay, thank you for your.
I was able to help you guys with this. Thank you very much.
From the ANC Council, I thank Sanjay Singh Tomor for your valuable guidance, and I hope all the questions will be clear from audience. So, dear all, we will meet at 2:30 for the second session. In the second session, we will covering the various plates, isotropic and composite plates, then Python scripting, impact modeling, and the user material subroutines, UMAT and VUMAT. Okay, so this session will be start at 2:30 and it will be up to 5 p.m. Okay, so uh, let's meet at 2:30. Okay, so now I'm ending this meeting. So thank you all. This session will be on YouTube live in future, on YouTube in future for your reference. So the same link will be used for the future for your reference. Okay, so thank you all for the attending the session. We will meet soon. Thank you.
Thank you, sir.
Yeah, thank you. Yes, Sumit. Sumit, are you there?
Hello, Sagrab.
Yes, Sumit. Good afternoon.
Good afternoon.
Okay. I just stopped my screen sharing. Okay. You just
Okay.
check your screen sharing and audio.
Okay,
volume.
let me do it.
Yeah.
Hmm. So is that okay?
Yes, Sumit. It is okay.
Okay.
Yes.
How is sound?
Yeah. Sound is also clear.
And now it is in full screen mode.
Yes, it is full screen mode. Yes.
Okay. And let me share another.
Yes. You.
Is it okay now, Abaqus?
No, Abaqus. You just share the Abaqus interface screen.
This is not visible.
No, just stop this screen and then you just again open this Abaqus.
Okay.
Go to again share screen.
How about?
Yeah, now it's okay. Okay, Sumit, most important, when you switch from the presentation to Abaqus, okay, please again share the Abaqus interface screen. Okay, you have to switch.
Yeah. Okay. I'll do that.
Yeah, okay.
Saurabh?
Yes, Sumit.
So how is?
Yeah, looks perfectly fine.
Okay. So can I start?
Sumit, we will wait for some 5 minutes, then we will start.
Okay.
Yes, Samet.
Yeah.
Yeah, I just introduced you. Okay.
What?
Good afternoon, friends. This is Saurabh from the Academics and Career Council. So the second expert is Samet. Is a Y16 PhD scholar from Ethiopia in the stream Structure Dynamics and Aeroelasticity, Department of Aerospace Engineering, IIT Kanpur. Before this, he has finished his BTech and MTech from Defense University College of Engineering, Ethiopia. He finished his BTech with a great distinction in the Department of Mechanical Engineering with a specialization in design technology. He also finished his MTech in Department of Aerospace Engineering. He has about 18 years of teaching various mechanical specialization courses, research work, and finite element modeling experience. Now his current research interest includes finite element modeling, damage modeling of composite structures, impact modeling, and analysis, etc. Now in the second session, he will be cover the 4 important topics, that is modeling of various plates using Abaqus CAE, isotropic and composite plates. Then second, how to generate and implement Python scripting. Third, impact modeling and analysis of plates using Abaqus CAE. And at last, he will be cover some important concept for the implementing material subroutines in Abaqus CAE like UMAT and VUMAT. Okay, so I welcome Samet for this session, and I welcome also all the participants for this session, second session. So now I hand over this mic to Samet, and I request Samet to please carry forward.
Interrupting. Is it okay now?
Yeah, okay.
Can I start?
Yes, please start.
Yeah, okay. There is some internet instabilities. I am observing it, but let me see. So thank you, Sabrab. My name is Samayat Fanta, research scholar, IIT Kanpur. I am from Ethiopia, Defense University College of Engineering. And this workshop is prepared by the collaboration of IIT Kanpur Aerospace Engineering Department, particularly Structural Analysis Lab. And my lab mate Sanjay has covered many important topics that relate to these finite element topics in our morning session. So he covered the following topics and he explained them thoroughly. He explained about the 1D bar elements, beam bending problems. He solved some eigenvalue problems with 3D plate modal analysis, meshing of geometries with some spherical void, and the 2 plate with hole. He modeled those plane stress formulation. So I will extend my lesson from this topic, and I'm directly going for advanced modeling, like plate modeling for impact damage analysis. So before going to the directly to the analysis, I will have some explanation on some important concepts. So basic objective of this presentation is listed as follow. To understand the finite element modeling approach for different materials and loading conditions, to develop stepwise impact model of thin structures and which include metallic or laminated structures when these structures are subject to some hostile loading condition. To explain the FEM procedure of damage modeling of fiber reinforced polymeric composite laminates with cohesive interface using Abaqus Explicit solver. To generate the Python script while running Abaqus files, or to implement the scripts to Abaqus model, to implement the Fortran developed user material subroutine codes like UMAT or VUMAT codes in Abaqus standard or in Abaqus Explicit. Some of the things are already how to implement how to get Python scripts from the Abaqus rand file. Anyways, let me continue with my discussions, and if time allow, we'll repeat it then. So it is better to start with a basic idea of what of any given physical domain or phenomena. So it is necessary to use a mathematical equations. So it uses comprehensive understanding of mathematics to quantify any physical problem domains like structural analysis, fluid flow analysis, heat transfer analysis, for wave propagation and analyzing the growth of even biological cells. So most of these processes are described in terms of some partial differential equations. So, so this partial, for example, for the dynamic analysis, we use such partial differential equation of a second order. Okay, so for the computer to solve these partial differential equations, many numerical techniques have been developed. Among them, finite element is the most prominent one. Why is finite element modeling is needed? Finite element modeling is used to simulate naturally or artificially occurring phenomena, and it is a foundation of simulation softwares. Most simulation softwares are derived or formulated after the foundation of FEM in order for engineers to assess their design for failure and damage in various loading conditions. Before just implementing the real object or prototyping or implementing stage. So that helps to reduce the expenses that we lost in experimental as well as prototyping, and it also reduces the time and effort. So this finite element, while we are talking about finite element, we have to understand some time-dependent or time-independent analysis types. Some of the analysis in finite element are time-dependent, others are time-independent. So for all nonlinear and dynamic analysis, there is incremental loads is needed. So we refer such problems as time-dependent problems when the effect of accelerations are pronounced and cannot be neglected. For such, for example, the drop weight impact case is the one. And we can also take other many examples. In case the effect of such deceleration must be accounted for in this case. In contrast to that, loads which are applied slowly onto structure surface, then the loading can be considered as either static, or we call it as quasi-static, or it is time-independent analysis type. So this is because the loading time is slow enough enough that the acceleration effects are negligible. Implicit versus explicit analysis. So these are the two most important analysis types in FEM. So both implicit and explicit problems are expressed using the mathematical partial differential equations form. And such partial differential equations are should be solved with in the matrix form, which are prepared with matrix form. So the computers can take them in the form of matrix. And these matrix equations can be linear or non-linear. So the most, this non-linearity of this thing appears because of different reasons. That the three most important cases of non-linearity in matrix equations are the material nonlinearity, the geometric nonlinearity, and the boundary nonlinearity. So some materials are nonlinear, that it experience the high deformation and the strain rate. For example, the polymeric materials are the best example for this. And the geometric nonlinearities are where their strains are small, but rotations are large. And such very thin structures are best example for this, like a thin sheet of aerospace structures and laminated sheets. The boundary nonlinearity arises from the contacts between two different components. So such nonlinearities will come in the matrix equation. Implicit finite element analysis. So let's see this implicit and the explicit separately. So one method of solving the unknowns that in our dynamic question, the governing dynamic question, the unknowns like acceleration u dot dot, displacement u dot, velocity u dot, and displacement to u are some unknowns in our most equations. So that can be solved using matrix inversion. For nonlinear problem, the solution is obtained in number of steps, and the solution for the current step is taken based on the solution for the previous step. So that because it is iterative process, and for large model, inverting such matrix, especially large stiffness matrix, is highly expensive and require advanced iterative solvers. This is also, we call it as a backward Euler integration scale. And these solutions are unconditionally stable, especially implicit solutions are stable and facilitate large time step. Despite disadvantage, this implicit method can be extremely time consuming when solving dynamic and nonlinear problems. So the implicit method should be used when the events are much slower and the effects of strains rates are minimal. So it is mostly suited for static analysis. So this is the some formulation of implicit dynamic method. So the governing differential equation is given in this form, which is given in terms of numeric algorithm. And from that, we can find, finally, the main case of this is we will go for the stiffness conversion here, or that stiffness matrix inversion. So that the stiffness matrix is very large, and it is not diagonal like as mass matrix. So that the conversion of that stiffness matrix is very difficult, and some other method, that explicit method, is used for dynamic problems. So here we have governing differential equation that mu dot at I plus 1 incremental time plus 1 plus alpha ku ti of I plus 1 minus alpha ku ti, which is equal to f ti plus 1 plus alpha delta v. So this is the governing differential equation in this implicit dynamic method. And the displacement is u of t at time I plus 1 is given in this form, which is expressed in terms of the numeric beta function. And also, velocity is also at the same I plus 1 time is represented with the numeric gamma function, relating the initial, velocity, the previous velocity plus time change with acceleration. And finally, the constant, the UMAT constant are defined in this form. So these are the Newman alpha, beta, and gamma functions. And applying the initial conditions, we'll go for the inversion of, here it is not mass inversion, but it is an inversion of stiffness. There is a correction here. This equation is not correct. We have to invert the stiffness matrix. Okay, actually this is to find acceleration. Anyway, another one is the explicit finite element analysis approach. With this analysis, which aims to solve for acceleration, in most cases, the matrix, the mass matrix is considered lumped. So inverting the diagonal matrix is very easier than inverting the stiffness matrix. So once the accelerations are calculated at the ith step, the velocity in I plus 1 over, that is a forward Euler iteration scheme we can use. So I plus 1 over 2, and then displacement is calculated at I plus 1 step. So this scheme is not conditionally stable, and smaller time steps are required. So the time discretization here is very small, which is needed to get accurate simulation. So to be more precise, the time step in the explicit finite element analysis must be less than the count time step. That the current time step means the time taken by sound wave to travel across an element. So the explicit method should be used when the strain rates and velocities are higher. That means most dynamic analysis need explicit analysis scheme. So just to explain the explicit analysis with taking some system with mass, spring, and dashpot, that will help us to understand the question. We are familiar with this type of system in our vibration course, and the governing differential equation is this type. Just when the system is excited with some external force from its static equilibrium position, then we can use some central difference method to find the acceleration. So we have this u versus t graph. On that, we discretize the time step into I plus 1 minus I minus, no, this is I minus 1, I minus 1 over 2. Again here it is I, here it is I plus 1 over 2, and I plus 1 time discretization is there. And this discretized time intervals are used for our calculation. So then from this, we find the velocity from the displacements are there. So velocity in the i's point of time, which is equal to u of I plus 1 minus u of I minus 1 over 2 times delta t, because from here to here, it is delta t plus delta t, that is 2 times of delta t. And the acceleration, okay, so u of I plus 1 over 2 is taken for u of I plus 1 minus u of I over delta t. U of u dot of I minus 1 over 2 is equal to ui minus ui minus 1 over delta t. So from these relations, the acceleration also found from displacement. And the most unknowns are now we are going to express the unknowns only in terms of displacement. Previously, there is velocity, there is acceleration, velocity, and displacement. But finally, we substitute all them at some specific equilibrium point, that i's equilibrium point. The equation will be changed expressed in terms of u only. That ui plus 1 and the ui minus 1 are the unknowns. So then finally, including those in the governing differential equation, finally we can solve it for acceleration. So during that time, most terms of the that finally we get the inversion of m. So our equation will be placed in terms of n. I can I can see it from here. So the final equation is acceleration is equals to this, okay? And in terms of mass, we can u dot of ti at equilibrium point of time, which is equal to m inverse of f of ti minus ku. This f of ti is the external force, and these are the ku ti of other part. So this is, and also implementing the initial conditions, that of t naught which is equals to u naught, and the u dot of t naught minus 1 over 2, which is equal to u naught dot. So applying these initial conditions, we can solve for the explicit dynamic analysis, solve for unknowns. So now, once we understand this concept, then we can go for some practical example, how we can implement this concept. Actually, that these concepts are the concept where Abaqus system designed for the analysis types. So I will start with some practical problem that we can first make an isotropic aluminum plate of some standard dimension, which I can call it as some standard. So with the same ASTM standard in the case of laminated composites, I'll do for that. And then we'll go for the composite laminate. So for that, here, the basic thing is what most structures in the aircraft body or in other case are exposed to external impact load from the surroundings or from the maintenance or that some activities performed on them, or while they are taking in the runways or so on. Many types of impacts are there. Maybe that classification is some vast concept, but let's consider some small impact that comes from foreign object on the structure. So that the impactor, let's consider that impactor as some rigid body and having some diameter of pi 16, let's take, and the mass of impactor taken 2 kg, and dimension 150 by 100 plate size with 2 millimeter diameter. So we can come to this 0.0 or 0.19 stacking sequence later, but first let's see for aluminum plate. That is okay. So let me start working with some aluminum plate. So let me share it. So I will start from scratch. I think there is some, your internet connection is unstable at size. Is it audible there?
Yes, perfectly fine. Yeah, fine.
Yeah, because here I am just observing some warning from the internet. So anyways, so let me start with creating a 2 millimeter aluminum plate with some spherical impactor of 60 millimeter diameter with 2 kilogram mass. So let me start.
Samit,
yeah.
Samit, if you are using Wi-Fi, then please
Yeah.
log in again, and then you start.
I'm using Wi-Fi, but if it is audible, let me continue.
Yeah. Okay.
Okay. So let me start with creating rectangular plates. So for that, we have to save our file in some particular folder. So let's create a set directory first. Okay. So let me. So impact problem. Let me select aluminum plate modeling. So this is the folder where I'm going to create my work or save my work. Okay, file. Now let's save the work. This is the always should be done. Yeah. Aluminum plate. Okay. So most of the things are already discussed in the morning session, so I don't want to explain anything on how this Abaqus module, what are modules, what are this property, module assembly, step, interaction, load, mesh, and so on. These are already what my friend Sanjay has discussed in the morning session. And also one can work it with the tree structure here, or someone can work with the module structure here. So I am going to use the module structure. So create part. Let me call it as aluminum plate. Aluminum. Okay. So 3D deformable solid extrusion, because I am going to extrude it to some dimension. So let me use metric dimension for that. So let me take this small screen grids. So for that, let me use, okay. Now, we have these geometric entities starting from point, circle, rectangle, ellipse, and so on. So let's select rectangle and create rectangle. Then provide the dimension to a rectangle. This is 150 millimeter. So minus 3. And this is 100. So let me, for easy assembly purpose, let me put it in at the center of that 0, 0 location. So let me move it. Okay. Yeah. Move, not copy, but move. Take this point and 0, 0. So it is now in its center. So extrusion is 2 millimeter. So 2e minus 3. This is a plate, aluminum plate with 2 millimeter dimension. And the next, let me create the part that impactor. So impactor is discrete rigid because we selected as rigid impactor. So let me create it from shell revolution. So take a circle and draw a circle. Dimension, take a dimension that radius. It tells us to specify radius dimension. So 8. Radius 8 selected, and then so we have to trim the extra. So this is 1/4 of the impactor. Then let's provide the angle of revolution, that is 360. Then you can see this impactor and plate. So we have two parts here. So the create module, we used create module here. Now this rigid impactor needs a reference point. So I have to assign a reference point for the impactor. So this is the point where mass of the impactor is concentrated on. For that purpose, we can, so let me assign reference point here. So immediately we can see ref here, RP. Okay, then what is the next? We have to go for property module. So on property module, we have to assign material property for both impactor as well as for the plate. So impactor is a rigid impactor that mass alone is sufficient for the impactor through some reference point. How can I? First, let me create some set for the reference point. Okay, create set, ref. So this is the point where the reference will be take place, and then the mass will be assigned through special inertia create point mass through this reference point, and then the mass is 2 kg because I'm using metric unit system. So I'm taking simply 2 in the mass isotropic blanket, and the rotary inertia portion will remain blank left. So this is mass property, and later density of aluminum, so that it is density is 2700 or 2707. It is, anyways, 2700 is the density of aluminum in kilogram per meter cube. And another material property of that aluminum is isotropic material. So for isotropic material, we can use this isotropic property. Okay, for others, we can use different material property here, but for aluminum, isotropic property only sufficient. So that let's use youngest modulus and the Poisson ratio of the aluminum. So the youngest modulus of aluminum is 68 gigapascal. Okay, and the mu value is 0.3. Okay, then okay, so let's create section, homogeneous solid section. Okay, so we have only one section, so let's simply take it as, and that is aluminum section, and assign section. So immediately the plate shows the material is assigned on it since the color change is there. Okay, so let's go to the next section, that is assembly module. So in assembly module, we are going to assemble two parts together. that plate is there. For that, I have to copy the move the impactor to the center of aluminum. So move, okay, through the point. I can select this point, okay, and then 200. That aluminum center point of aluminum is 00. So the impactor is now in 00 position, and I have to rotate the impactor to proper location because now it is. So how can I rotate? There is rotate instance option here. Okay, let me click on the impactor and then select the start point for the axis of rotation that I can rotate this impactor about x-axis. So I can take any point in x, for example, 10 and minus 10 points in the x-axis. So and the second point is minus 10, and then 90-degree rotation by default. Let me check. So in 90-degree, it rotated. Sorry. Yeah, it is rotated properly in the position. So that is okay now. So I can say okay. So now the plate is in its proper location. So someone can offset the impactor from plate for a very small gap. That is possible, or it can be there, no problem. And once assembly is done, we have to go for. So step module helps us to define different parameters. One is, hello?
Yes, Amit, what happened?
Yeah, any problem?
No.
Okay,
Fine.
okay.
Please.
So step module helps us to define the type of analysis as well as the required outputs. What output we need from our analysis, that should be defined in the step module, and the analysis type. So for this, I can use, let me create a step. Then it's by default, it is static general with procedure type general. Okay. So there are two options here. In the morning, my friend Sanjay discussed on the linear perturbation portion, but now for our purpose, the analysis type is not static, but it is dynamic explicit analysis. For dynamic explicit analysis, I can use a general type of. Okay, so this is dynamic explicit analysis type is selected, and here I have to specify the impact time period. So most of the time in impact analysis, the time period is very small that impact happen. So let me take it as 0.006 second, or that is called 6 millisecond. Okay. And make sure that nonlinear geometry is on, that NL geom should be on, then okay. Then here I have to specify I need some impact velocities, different history outputs, and other parameters. For that, we can go to create this output thing. Okay, but we can come back for this after defining the contact. So the next one is interaction. So interaction is also another important module in such contact problems. So for that, let's take a general contact for explicit analysis. Okay, for explicit analysis tip, general contact is appropriate. And then let's define the penalty friction of some amount, that friction in between the plate and the impactor. There should be some friction on that. And the normal contact or the normal behavior should be hard contact pressure over closure and taking a default constraint enforcement. Okay, so let's define this. So let's make some interaction between the plate and the impactor. In this case, there is no such complicated interaction because there is no plate-to-plate interaction, but it is only impactor-plate interaction. So we can make it even surface-to-surface contact explicit interaction, no problem. We can make actually. So let's define the first surface as impact surface. That brown color part is the normal outward of impactor. And let's select the second surface as the top of the plate. So then the interaction is finite sliding interaction is taken. And we can take this. Okay. So interaction is already done. And let me come back to the step module and let's define. So create history output. Okay. Contact history output for the okay, for the set that I set impactor reference point as a set. So that set must from the point where the set is there, we have to extract the U3 output, displacement of the impactor, the velocity of impactor, and also the acceleration also we can find, and also the reaction force. RF3 is sufficient. And then let status on the damage or the yeah, okay. And then here let's define the interaction output that I need contact stress, okay, contact force at the point of interaction, okay. So these are sufficient for the time being, okay. Now the next is load and boundary condition. That is the second module. No, the next important part of our work. Sorry, this thing disturbing a lot. So how can I define? Let's create boundary condition. Plate must be either supported with simply supported boundary condition or clamped boundary condition that substitutes the experimental clamping and the base support. So for that, let's take some simply supported boundary condition. So for that, let's call it as SSS. And for this step, mechanical, symmetric, anti-symmetric, and then caster. So let me select the 4 corners of the plate. Sorry, this is not. Yeah, the 4 corners or the 4 edges are selected, and then I want to constrain it for U1, U2, and the U3 only, so that pinned condition is selected here, or one can use Impactor condition actually, that fully constrained condition, that constraining all 6 degrees of freedom of the motion of the plate. And another is we have to constrain the impactor also to move only in the Z direction, because the motion of impactor is expected in the Z direction. So for that, let's displacement of the impactor as, okay, mechanical displacement. Okay, so let's select the reference point. Then select these other 5 parameters except U3. Okay, then okay. So now the impactor is constrained to move only in the Z direction. One thing which I must add in the interaction model is I have to define the constraint for the impactor, because impactor is a rigid body and it should be constrained. So let's create constraints, rigid body. Okay, continue. Then body element. Okay, edit select. So select the impactor and show through the point where the motion is constrained. So that is the point where motion is constrained. So this is what. Now what is left? I have to give velocity for the impactor, because already mass is assigned through the reference point, and velocity should be assigned for the impactor. So how can I? So we can give using create boundary condition option, or we can give it using create predefined field. So let me provide through create predefined field. So let's select initial. Okay, so mechanical velocity. Okay, so through this point, now I'm going to give the Z velocity, that V1, V2 remain blank, remain left as blank. So let the velocity, let's take that 3 meters per second. Okay, so V3 is 3 meters per second. Let's see. Yeah, it is in the right position. You can see the impactor is, the movement of impactor is in the direction towards to the plate. So now boundaries and constraints are done. What is left? Meshing the part and selecting the analysis, or either static analysis. No, I mean either standard analysis or explicit is left. Okay, so now let's make a mesh on the part. So many things about mesh is already clarified in the morning session, so I don't want to say anything on that. So let's make a global seed. So global seed, let's change the seed some 2 millimeter. Okay, apply. That is very okay. That is okay. Let's take let's take 3. Yeah, it's okay to make, because we are going to take rough work. For that, 3 is sufficient. And then seed edge option helps us to make some particular refined mesh on our work in some critical regions. Anyway, so let's mesh it. Yeah. So the plate is now meshed, and let's select the material type or assign element type for the plate. So select the plate and go to 3D stress case, explicit. Okay, so linear geometric order. So here also my friend Sanjay discussed this linear, what is linear, what is quadratic, and so everything is discussed in the morning. So actually, yeah, so 3D stress case, C3 D8R, that is 8 node linear brick reduced integration element is selected. Now, okay. So the next is impactor. So for impactor, it is a rigid body, so no need of we can simply mesh it, but no need of assigning that elements and other things. So this is an impactor mesh. So finally, what we are going to do, that part is done, property is assigned, assembly is done, step, interaction, load, mesh, and the next is job. Just go to job and create job with some aluminum plate, or you can give any name. Okay, so then okay. So here we are not using any user material subroutine, so we directly say okay. But if there is some other material subroutine that we implement to this model, we have to click on general, and here there is an option for user subroutine file. So that we can click on the folder of user subroutine file and implement into this model. Anyways, what we are using is directly the inbuilt Abaqus system. For that, we directly say okay. So this is the plate model. So finally, we submit this work. So let's check for the data whether it is what I'm done is correct, or if any mistake on my modeling steps. Let's check. So still there is no warning. That means what I've done may be correct. Sometimes when we are modeling or when we are creating a model, we might miss a silly steps on somewhere, and the system will terminate or abort with error. So that's why I'm checking it. Anyways, while it is checking, let me go back to my this presentation. Means to my this thing. Okay. Sorry. So the next, as we can run it, no problem. But the next part of our work is the on laminated plate. So let me discuss on laminate plates until that aluminum plate run, because this dynamic explicit analysis, most of the time, it takes time. And it needs high computer memory. And in my case, my laptop is not such sufficient for this analysis. Anyways, until it makes a run, we can discuss on the how we can model the laminated plate. Okay, so our laminated plate contains 090 stacking sequence of symmetric plate.
Samet,
And yeah.
Yeah, please share the screen presentation.
It is okay. It is not visible.
No.
Yeah,
No.
sure. Okay, I will do. I will do. Okay.
Yeah, now it is visible.
Yeah. So this is 150 millimeter by 10, 100 millimeter by 2 millimeter laminate plates of 090 stacking sequence of symmetric plate. And also, I will try to incorporate the interface in between two layers, because whenever this 0 and 90 or lamina with different orientation comes, delamination phenomena happen on the laminate structure. So that will be included into the model using an interface layer. So I will use an interface layer in between our model. So how I can do? Okay, that these all steps are what we have discussed practically.
Samet,
yeah.
Samet, the check is completed. You just submit the job and then you again come back to the presentation.
Okay, okay, okay. So let me submit. Once the check is completed with no error, then I can submit. Okay, submit the job. Okay. So after submitting, we can check many parameters. If there is error on that, if there is some other missing things, that can be checked with the help of monitor. You can monitor your job like this. So everything is done in the morning session. So for me, it is highly facilitated. And there are some harmless warnings most of the time appear on this. There may be some different warnings come that are not harmless. If the warnings are harmful, then it terminates with error. Okay. So we can even check the outputs, check the data files, they check the message files, the status files here. Anyway, this is a monitor dialog box. Okay, so let me come. Yeah.
Yeah, if you want to go with the Abaqus interface, just share the Abaqus interface.
Okay, okay. It is still interface. Okay.
Yeah, it is still PPT.
Okay. Why this is jumping like that? So
yeah, we have to,
am I in PPT now?
Yeah, you are in the PPT now.
Okay, okay. So let me share Abaqus interface. So now Abaqus is running, so we can monitor many parameters here. Okay, error, if error is there, warnings, output. Okay, data file, message, stats file. Okay, so now it is there is some harmless warning, as I told you. There are one warning message in the .dat file, please. So that maybe not affect our work. So it is running properly. So we can see, yeah, I think this running is completed. So it is complete. So we can see a result of this. So this is undeformed shape of our impactor, and so let's see the so let's see the contours plots of contour. So this is the plot of contour. And we can also animate. Okay, so on that we can see the parameters which we specified. For example, U, the deformation. Okay, and we can simulate it like this. Okay. We can see different stresses. Okay, S1, S2. Okay, and also we can see the history outputs of the simulation. Okay, we can go to output database, and we can find the job name itself of the ODB file here. On the ODB file, you can find this history outputs. So on that, you can see the kinetic energy. So this is the kinetic energy, because I used that 2 kg of mass and the 2 meters per second velocity is 2 meters per second, mass is 2 kg, so that the energy calculation is half mv square. That is in experimental work mgh calculation. In experimental setup, the impact model will be calculated with mgh. That h is the height, mass is mass of the impactor, and the height of the impactor should be set to some specific height from the surface of impacting plate. So that calculation will be also done here. And here the initial kinetic energy is dropped down here. So the initial is not completely returned back. This implies that there is some energy dissipation during impacting. The amount of the remaining size from initially it is about 8, 9, yeah, it is about 9, or we can calculate it, it is half mv square. Half mv square means, okay, v is 3, I think, yeah, I give 3v, so that is 9, energy is 9. Mass 2, velocity 3, so it is 9. So finally, it is about less than 6, means about 4 joule of energy is dissipated by impacting. So that is the amount of damage happened on the structure, it implies. Okay, we can also see the deflection. So this is the deflection of the plate the plate impactor interface points, that central deflection. And also one can see the velocity and so on. And also we can see other parameters also. So this is about the aluminum plate case. Okay, so now let me go for composite plate. The case of composite plate is not such easy as we have done here for aluminum, because a lot of interaction things are there, and a lot of physics also comes on that. So let me go to my slides and discuss on some issue of the aluminum plate. No, not aluminum plate, but the composite case, because we have to know the materials applied to the plate, to the interface, and so on. So what are the materials? This creating and other thing is already what we have done practically. So we have to create 0.25 millimeter plies. Okay, 0.25 plies, because or for example, in our case, it is 2 millimeter. To get that, we need 8 plies or 8 laminas. So rather than I can use 5. So that has actually an effect in the result. Anyways, I will use 5, and I will take only 4 plies. Okay, so 0.5 millimeter I will take, and the interface of 0.02 millimeter. So I'll create. Okay, this is creating, defining the mass. So let me come to the material property. Sorry, this thing is disturbing. So materials used in composite plates are not simply taking the Young's modulus and the Poisson ratio of the two, property and density. Here we need more materials because this composite is anisotropic, as all of you know it. So it needs elastic properties. Okay, different elastic properties are there for different material. I'm going to use for particular T700S M21 standard carbon epoxy property, for which these are the material properties, and the strains properties are given as like this. Okay, and the fracture energy, that the fracture energy properties, and also density is taken as like this. And the next is the interface property. So interface layers are required to implement to simulate the delamination case. These laminated composites are severely affected because of delamination at the interface when there is two plies of different orientation. So that delamination properties are also required. For that, interlaminar allowable strengths of interface, penalty stiffness properties of cohesive layer, and interface fracture toughness are required. Okay, and there are some signs of that interface layer. How damage initiate on interface layer is also be there. Most of quadratic stress criteria for delamination initiation is applied. Okay, so this material related with this one, and the penalty stiffness is related with the uncoupled stiffness, the diagonal stiffness matrix. It is related with this, and it is of the traction separation condition. So this also all will be incorporated to the model. And then we have to implement these material properties based on in the Abaqus built-in system, which is incorporating all the hashing criteria for the failure or the fracture of fiber reinforced composites. So Hashin created some formulations in 1973 and 1980s, which is directly incorporated to the Abaqus built-in system. And whenever we need more than that, and when we want to implement some physics of this damage, we must write these properties in a separate text, separate Fortran code that is known as either UMAT or VUMAT in our case. But for different fields, the name may be different. But in our case, we incorporate these properties using user material subroutine VUMAT or UMAT. But if we are happy with only the built-in system, these formulas hold true in Abaqus. Okay, so fiber tension, the 4 damage case in the Abaqus fiber reinforcing composite material is fiber tension when this condition is hold true, that sigma 1 greater than or equal to 0. Then this formula is for the fiber tension. For fiber compression, when sigma 1 less than 0, this formula holds true. For matrix tension and matrix compression. Okay, so this is incorporating the Abaqus damage parameters to our model. And actually that the alpha here is some parameter which is 0 when we are implementing Hashin 1973 approach, and it is 1 when we are using 1980 approach, which incorporates the shear stress to the fiber tensile initiation criteria. Okay, so other parameters are already known. So we'll incorporate this all in our model, and the damage evolution on the structure is related with such science, which the effective stress in the material is equal to the damaged stiffness matrix after the damage happened times the strain. So what that damage stress, that we can write it in different ways. For 2D, for 3D case, this formula is different, but this as a sample I represent it. Okay, and on that we use some damage variables that incorporates the stiffness degradation in the material. Okay, so different damage parameters or damage variables are incorporated. That for the fiber damage, for the matrix damage, for the shear damage, different damage variables are implemented or are used in the system. And how the damage evaluation take place, that we will see them practically one by one. So when you create the damage initiation criteria, we select the sub option. On the sub option, we implement all the damage initiation criteria. Again, we select the type of damage evolution, either displacement based or energy based damage initiation criteria. Most usually we use energy based damage initiation criteria, and the softening method should be selected, either linear, exponential, tabular, or any one of. So the most usual is the linear softening method that shows the traction separation of the or it indicates the material stiffness degradation, how the damage initiation occur. For example, in this case, this region of the line indicates that the stiffness, that linear relation of the stiffness. So the slope of this line is still constant to here. And once one of the damage initiation criteria is satisfied, or that D reaches to value 1, then it starts to degrade, and the stiffness degrading to final failure point. So until delta naught, the damage is not initiated, but once it arrives to delta naught value, for ultimate strength or ultimate traction, then the stiffness degradation starts, and finally it will fail at this point. And that point maybe is the failure point we call. In case of exponential damage degradation, the exponential damage degradation curve, as you see, the curve is exponential curve. In the first region, it is still linear. Okay, so this type of expressions are there. Select mixed mode behavior when we are using cohesive elements. That mood independent, tabular, power law, BK criteria, these are there in the Abaqus system. So most of the time we use either the power law or BK criteria that Ben-Segak and Kenan formulated this formulation, where G1C, sorry, this is G1C, this is not GC. GC is equal to G1C plus G2C minus G1C. As a whole, G1 plus G, this is also G2. Okay, this is G1 plus G2 over G1 plus G2 plus G3. These are G1, G2, G3 are the fracture energies, and these are G1C, G2C, are the critical energy release rate. These are critical energy release rate, and this is the BK coefficient that is obtained from the experimental for most material. And when we are implementing energy criteria, we have such a formulation. So this alpha value is 1 to 2. Okay, for alpha, for coefficient alpha value 1 to 2, and this zeta value is obtained from experimental curve fittings. Okay, and select the degradation. So either maximum or multiplicative degradation. So most usually by default we use maximum degradation approach. And then select mood mix ratios. As I told you that for energy, this mood mix is of alpha value is 1 or in between 1 to 2. Actually, this traction is most of the time that quadratic traction. This formula comes here wrongly. Anyways, okay. For the Hessian damage, we also implement this tensile fracture energy, compressive fracture energy, tensile fracture energy for matrix, for compressive fracture energy for matrix, also implemented on the table given. So we'll see this one by one in practical one. So let me go to the practical session. So let me go back to the model. Let me start with blank. Okay. So let's save our file. Okay, file, set directory. Well, I start with setting directory because you must place all your work in some proper location. Okay, let me put it in some impact simulation. Okay, this is impact simulation folder. Right, I'm going to save my work on that and save as. Let the name same name. Okay, let me simply say simulation. Okay, on impact simulation folder with the name simulation. Okay, so let me create 2 plates with dimension 0.5 millimeter thickness and the standard ASTM D300 37136 standard. That is a standard dimension actually. So create part. Okay, 3D deformable. Okay, solid extrusion. Okay, still I'm interested to use metric unit system in order to avoid confusion of that tone and other parameters. Okay, so instead of kg in other dimensions, especially if I use millimeter, in place of mass, I have to use tone and other things. So that makes some confusion on work. Okay, so let me create a plate of dimension 150. Okay, so this dimension is 150 e minus 3, and this dimension is 100 e minus 3, and then okay, so still it is out of plane too low. So for easy assembly, I have to bring it to center. Okay, that facilitates the assembly process. I'm using simple construction line. Okay, this is construction line, so it is not such. So let me move it. So move. Then okay to 0, 0 position. Okay, so now the plate is in 0 position. with dimension 150 by 100. Okay, so extrusion is 0.5. In actual, this dimension is in lamination, it is 0.125 order. Most of the laminars are created with 0.125 and like that. But I'm just using this as rough work because we cannot stack those all placed in this lecture. So one can make the dimension of 0.125 and less than that. Okay, so E minus 3. So this is thick lamina. It is not very thin. Okay. Okay. Then, so in order to use our time, rather than just doing the same procedure 2 times, I will copy this copy and name it as 90 plane. The name 90. And the previous one is simply part. So let me rename it as 0. 0. Okay. So I have 2 plays. And I want to incorporate interface layer also. I want to incorporate interface because here we discussed how the interface materials are there. So let me add interface of a thin layer, which is approximately less than 10 times of the thickness of the play. Okay, so let me copy this and reduce its thickness, interface. Okay, so let me go to interface and extrude. This extrusion, let me make it as 0.005. Okay, that 1/10 of the thickness of fly, or it can be less than that. Okay, so this is interface, and what left? Impactor is required, so we have to create an impactor. Okay, so still I'm using a rigid impactor. So create. Let me give the name impactor. So discrete rigid. Okay. Shell revolution. Okay, so let me create the same size as before. So let me do some dimension for this. Okay, that is 8 E minus remains, radius 8. And let me make some impactor of geometry. And the trim necessary lines. This is the line. Let me trim this also. And then this should be revolved to 360. Okay. So then, yeah, 360. So finally, we can get this impactor. And let me give a reference point to the rigid impactor. Okay, this is the reference point. Immediately you can see some RP on that. Yeah, so now modeling thing is over. We created 4 parts. The impactor, 90 lamina and 0 lamina, and the interface. So all of them are here. All those parts are here. So let's go to the material part. Material. Okay. So here, the material, the only material for the rigid impactor is the mass. So let me give mass to the reference point. So let me provide some set. Sorry, this disturbing. Okay, set, great. Okay, reference set. is created here. Yeah, done. So special inertia, create, okay, point mass, because what we are using is lumped mass, that diagonal mass matrix. Actually not that case, but this is a point mass, actually concentrated mass, okay, through the reference point. And let's use the same dimension of mass, that is 2 kg. Okay, done. So we can see some green color that implies a point mass is there on that reference point. One can calculate the point of center of mass for this geometry, okay, and then place this mass to that point center of mass. And the next is the composite lamina, okay, lamina property. So let okay, for the lamina general density. So let me give density of 1600 for some carbon material. And here, if we are creating 3D solid laminate of solid element, then we have to create the user material. If we are going to implement the user material subroutine that created in Fortran language, then we have to provide all the material property using user material here. In this user material, for example, let me, I'm not going to use that, but let me show you user material. Here, you can implement the material property. For example, I am going to implement, if I am going to implement some hashing criteria and all important parameters which are not fully obtained from the Continuum shell, because that Abaqus online, that built-in Abaqus system enables us to run either the conventional shell element or Continuum shell element only. But if we are using further, that Continuum and the conventional shell element will not display the through thickness damage parameters, or through thickness damage things will not be easily obtained from that. So that when we are incorporating that the through thickness parameters, then we have to use the user subroutine file. We have to create Fortran written or Fortran language written user material subroutine. For that, we have to give all material property. For example, we can give even some use the same. Okay, again E3 10.3 E9. Again, the Poisson ratio in 1 direction, let 0.2, in 1 2 0.32, in 3 0.0. Sorry, Poisson ratio in 2 3 direction 0.4. Then the shear stress 1 2, for example, let's take 80 gigapascal. Okay, 18. No, that is not shear stress, but the shear modulus G12. G12, for example, 6E9. 6E9, that is G12 and the G13 taking the same, and let G23 as 3.8 E9. This is a material property of one particular carbon epoxy combination. And then other parameters like the strength parameters should be specified also. Okay, so, and also the energy parameters. should be specified. Then this will be remain as it, and then we have to specify the solution dependent state variables. Deep var should be, for example, let me say here some 10 and some 5. So this thing alone will help us to model the three-dimensional composite model. So now let's go to the continuum. We are going to model with continuum shell element, because my computer system is not such licensed one, so that I cannot run the VUMAT code in my system. So for that reason, I am going to use the continuum shell element with the Abaqus inbuilt system. So let me remove this deep var and user material. Okay, so density is there. So what is I'm going to do is, let's go to mechanical, elasticity, elastic, and then elastic type. Here we have isotropic that we used for the isotropic aluminum plate before. Now I'm going to use either engineering constant or laminar. Okay, there are also another options, orthotropic and isotropic. So I'm going to use engineering constant. Okay, so when I select engineering constant, you can see here E1, E2, E3, new 1 to new 1, 3, new 2, 3, G1 to G1, 3, G2, 3. So this new E1 for the particular material which I have discussed with you is 135 gigapascal. Okay, E2 is 10.3 gigapascal. This is also 10.3 gigapascal, and the new one 0.32. This is 0.4, and this is 6 gigapascal. This is also 6, and this is 4. Okay, so these are elastic properties, and then the Abaqus built-in is designed with hashing 2D criteria, so that I have to implement the that strings parameters through the hashing 2D criteria approach. So for that, mechanical elasticity, no, mechanical, go to damage for fiber reinforced composite. Okay, under mechanical you can find damage for fiber reinforced composite. Then select hashing damage. Okay, select this. Immediately what you can see, longitudinal tensile strength, that's XT, longitudinal compressive strength, that is XC, transverse tensile strength, that is YT, transverse compressive strength, YC, longitudinal shear strength, SL, transverse shear strength, ST. These parameters are there, so I will implement these values. The longitudinal tensile strength, that XT is 200 and 2,500 megapascal. Okay. This longitudinal compressive strength is 1,250 megapascal. The shear is the transverse tensile strength, that is very small value, 60 megapascal, yeah, E6. Sorry, here I used 1,250 giga, but it is mega, so E6. And transverse compressive strength is 236 E6. Shear is 80 E6. And this transverse shear is some 70 E6. So these are the material property of some particular carbon epoxy material. So now the alpha value here is, if I am using that the Hashim criteria of 1973, then it will be remain 0. But most recent one is the 1980, so that alpha value is 1. That accommodates the shear effect on the tensile strength. And then we'll go to the sub option as we have discussed in the slide before. So, so let me click on sub option. Then we can see damage evolution and damage stabilization. So damage evolution implies the damage of fire in the system. So then let's consider damage evaluation. Okay, so here we can see 4 parameters: longitudinal tensile fracture energy, longitudinal compressive fracture energy, and transverse tensile fracture energy, transverse compressive fracture energy. And the damage evaluation type is energy based. Softening is linear, as we have discussed. Okay, linear softening, energy type, and fracture energy in the longitudinal direction is. I have to go. Okay, I have to see from my slide. That is okay. Yeah, the fracture energy. Fracture energy is 133 Newton per millimeter, 10 Newton per millimeter, 0.6 Newton per millimeter, and 2.1 Newton per millimeter is the fracture energy. So that I'm going to 133 E3. Why? Because it is Newton per millimeter. So that should be Newton per meter. Okay, what I'm using is SI unit. This is 10 E3, 0.2 E3, and 2.1 E3. So these are the fracture energy. So we already now assign the Hashim damage criteria to the lamina. What is left now? Yeah, this lamina property is already assigned, and we have left an interface property. So we have to create an interface material. So interface. So give density for interface. Let it is 1,300, and mechanical property, elastic property. Interface is considered with the traction. Okay, in isotropic, we select that traction. Uncoupled traction is there, and coupled traction. So traction property is selected. So in this, the values are already given there in the slide. That is 10 E12. That is considered. Okay, 10. Actually, it is more than that, but we can calculate it using Turon formula. So for Turon formulated for this thing, that the values of these entries are proportional with alpha E3 over T. Alpha E3 over T means what? Alpha is some value. Turon took some 50 is alpha value. E is the E3 is the youngest modulus in the 3-3 direction, and the thickness is the minimum thickness of the adjacent place. Anyways, we are taking approximate value, that is 10 E12 for all. And then what is left? This interface is characterized by damage for traction separation law. So on that, Quadratic damage initiation criteria is considered from our previous lecture. So let me take quadratic stress damage criteria that is considered. And on that, nominal stress normal only mode, that is strength in the z direction can be considered. That strength in z direction is 60 E6, 60 megapascal at y tensile, because in our first mode of fracture, especially in double cantilever beam approach or other approach, in the first mode, that YT is considered for the nominal stress only on the only normal mode. In shear direction, we consider the longitudinal shear value, 80 E6, that is 80 megapascal, and also 80 megapascal here also. So these are first shear and the second shear and nominal. So these values are taken. And you can come to option for damage evolution of the interface. Look, so here, damage evolution of interface, we discussed these points there. So displacement or energy type. So we select energy type. That energy type of analysis is best suited and gives better result. Softening linear, exponential, and tabular. We already discussed this thing. So let's take the linear softening. That the graph of the softening graph, which goes down until fracture, from initiation to fracture linearly, degradation maximum and the multiplicative. So the default maximum is taken. Mixed mode behavior is mode independent, tabular, power law, and the BK. So the most formulated one we have are power law and BK criteria in most research works. So let me select the Benizagag and the Canon mixed mode behavior BK. And then the BK power coefficient, that gamma value, let it be 1.45, which is for particular carbon epoxy material. And the nominal mode fracture energy in this case is 0.2 E3, that already given in the table on my PPT. And this is 2.1 E3, 2.1 E3. So these are the values of critical G1C, G2C, G3C, that critical energy release rates. Okay, so their values are here. Okay, so now, okay. So these are density, elasticity, elastic behavior, quadratic damage initiation, and damage evolutions are defined for the interface. Okay, so now the interface properties are created. So we have to implement these properties. So for the interface, let's create a section. Okay, create section. Okay, then here there is no interface thing, so that we click on others. Then we can see this gasket, cohesive, acoustic, infinite, acoustic interface. So cohesive is our case. Select cohesive. Then the material type is interface, that already I given this name interface, and the response is traction separation response. Traction separation response. And we can take the remaining default settings. Okay, so let me assign this section. So this interface layer is assigned with section, and this is the interface. And then the 90 and the 0 place, we can provide material for 90 and the 0 using either here composite option or we can use this composite layup. So let's use this composite layup option. And on that, by default, it tells us for ply count 3. So let's take it a 1. If we are using only one ply to model the whole plies, we can take this number to 3. We can take 3, 4, 5, or depending on our number of plies. But I want to model it one by one. So let me take the ply count as 1. And there are 3 options: conventional shell, continuum shell, and solid. So let's take continuum shell. So continuum shell will evaluate the 2D this plate element in better way than conventional shell. So that let me select. So continue. And here it asks us to ply name. Okay, you can give it as 90. For example, here I selected 90 ply. So let it be this be 90. Okay, you can give the name. Region on the ply, select this region. Okay. Then material. So we have interface and the lamina material. So lamina is our material. So, and relative thickness, let's give it as the almost same thickness with what we have given. Okay, 0.5. Okay, and angle of rotation, that is 90 for this one. Angle of rotation is 90, and by default integration point 3 is assigned to this material. Again, for 0 also, we have to do the same thing. Okay. Yeah. Name, give the name 0. 0 region, select material, that lamina material. Okay. And angle of rotation 0. Yeah. So now all materials are assigned material property. And then what is the next? That is assembling of these parts. Assembly is the next. So I have to be very fast because so how we can assemble? Okay, create, assemble. Okay, so the stacking sequence is 0, 90, symmetric. So 0. Okay, just check on this auto apply. Okay, in between 0 and 90, interface should be incorporated. Interface, apply. Again 90, apply. 90 will repeat 90 because 0, 90 symmetry means 0, 90, 90, 0. So 19 apply, then interface apply. No, sorry, I made, I think, mistake. The sequence is not impactor. No, let me go to assembly and I can see what I have done. 0 interface, 90 interface. No, interface will I'll implement interface only plies with different orientation, but 90 and 90 in between 90 and 90 interface is not required. So let's apply 90. Okay, then interface will come again, then 0, apply, and then impactor. Okay, so 7 parts. 1, 0 interface, 90, 92, 90, no, interface 2, 0 to end impactor. So these parts will be assembled to get a proper model, that laminated plate model. So how can I do that? Okay, let me take this thing away from my working environment. It is disturbing. Okay, so let me select move this interface. So please be patient. It might take some time. Okay. Let me put it here. So now 0 interface is assembled. Again, let me bring 90 over interface. Okay. So now 90 interface 90. Copy this, not copy but move. Okay. Again.
Samit,
Yeah.
Samit, I think for the zero layer, you said the thickness 0.5 into 10 raised to 3. That's why you check it.
Which one?
For zero layer.
Zero layer.
Yeah, you check the thickness.
Thickness of 0.5 millimeter.
Yeah, it is by mistake it is 0.5 e raised to minus 3. So you place 3.
Yeah, it is e raised to minus 3 because I am using metric unit.
But it is minus 3, but by mistake you take as a e raised to 3.
Okay, I will check that.
Yeah.
Okay, before I complete the, okay, let me see. For zero layer. So other also taken from 0. If 0 is not correct, others are also not. Yeah, that is correct.
Correct? Okay.
Yeah, that's correct.
You check for 90?
90 is a copy of 0.
Okay. Then
so 90 is copy of 0, no problem. I
Okay.
copied it and only provided name 90.
Okay. Because one of the student asked the question like that. Okay, thank you.
Yeah, okay. No, it is I copied 0 line layer, and only I provided name and that what you call orientation only.
Okay, please go ahead. Thank you.
Okay. So this is the place of 0 interface 90 interface 0. So this is the stacking, and sorry, come back because I didn't specify it. Okay, move. Again, let me move interface, no impactor, from this point to 0 position. So this is the assembly. So let me make rearrangement on impactor. Let me rotate impactor in x-axis. Okay, so same as what I have done in the case of aluminum plate. Yeah. Okay, so now it is properly positioned. So this is the assembly of both impactor, interface, and 0 layer. So we can see the plate like this. Okay, this is assembled now. The next step is okay, or can I do this? Okay, So let's go to step. The next is the step module. So in step module, I have to also give analysis step. Okay, that is a dynamic explicit step, dynamic explicit with general procedure. Okay, continue. So let me give the same time 6 milliseconds. Okay, and so in this case, we applied the damage in the laminates as well as in the interfaces. So we must request for output of this. What are those outputs? The hashing 3D, the hashing damage outputs must be requested here. Those are the matrix damage intention, matrix damage in compression, fiber damage intention, and fiber damage in compression. That satisfies the hashing damage initiation criteria. That must be requested here. For that, let me go to create output, that field create field, okay, field output. Okay, so let's okay, energy, no energy actually, failure and fracture. So tensile damage, compressive damage, again fiber tensile damage, fiber compressive damage, matrix tensile, matrix compressive damage, shear damage should be requested. We have to request for scalar stiffness degradation. Okay, so damage initiation criteria, that to initiate the hashing damage initiation criteria, all these hashing fiber tensile criteria, hashing fiber compressive damage initiation criteria, hashing matrix tensile damage initiation criteria, hashing matrix compressive damage initiation. This should be initiated whenever I request for damage initiation criteria. In addition, we have an interface layer that is to account for delamination. For that, I have to select this scalar damage, scalar stiffness degradation for cohesive surface. And the quadratic stress damage initiation criteria is implemented so that I have to select the quadratic traction damage initiation criteria here. And then the status should be on. Okay, this status should be on. So this is the output request. So whenever we create something, we must request for output for that. Unless we cannot get, after running the file, we cannot get these things. Okay, so then what is left? Let me take, okay, history output for the impactor, because we set some reference point on the impactor. Through that reference point, we need some output, that is the displacement graphs, acceleration graphs, contact force graphs should be obtained through that point. So let me request domain set and through in the reference, that is reference at the point where I specified for output. So let me request these things here, as we have did it on previous lecture, or on the that V3 and the U3 are our requirements. That's why I'm selecting them. And I need contact reaction at that particular point. Okay, FR3. Yeah, so this should be requested here, unless we cannot get after running the file. Okay, so the step is done. Now let's go to interaction. So now here there is a complex interaction will come. What we have discussed, the nonlinearity of this contact nonlinearity will come. We have a rigid impactor and we have deformable plate. And also we have deformable plate with deformable interface layer. So a lot of complex nonlinearity of the material as well as geometry also comes here. So that's why the analysis is a nonlinear analysis. So let's define the interaction also, that general interaction type. Okay, general contact for explicit. Let's define it as some tangential behavior as friction with some 0.3 and normal behavior as hard contact with allowing the separation of after contact is allowed. Okay, and let's provide some fake property with no because I'm going to provide the contact pairs of the plate and the impactor separately. So for that, let's create some fake property. Okay, with I don't give any material property here. So let me come out from here, unless it will not allow me to come out. Okay, so let me go. Now my impactor is directly connected to the surface, so that will cause some disturbance. So let me move the impactor somehow above the plate. So let me move it. Okay, let me select this impactor. Initially it is in 0, 0 position. Okay, from 0, 0 position, our z direction is downward, so that in minus z, let me bring it somehow 0.01. Minus 0.01 means in the z backward. Yeah, it is now not directly contacted with the plate. Now let me make, okay, so find contact pairs. On find contact pairs, let this include first separation tolerance. Let's make it like this. So here an option for find contact pair. Click on that. Then you can see the contact pairs here. This contact 0 interface, correct. Interface 90, correct. 90, 90, and 90 interface, and finally interface 0. These are the contact pairs of the plate. Okay, so let's say these contacts are a tie contact. Okay, let me tie them together. Okay, surfaces are now in tie constraints. Okay, so all the plate and the interface layers are properly tied to each other. So actually, it is possible to define multiple constraints or multiple interactions, but this is somehow sufficiently we can simulate our work with this also. So now, what is left? I have to create constraint for the impactor also. Our impactor is rigid impactor, so that it should be constrained as a body element. Okay, yeah, and the reference point for this body element is here. Okay, yeah, now done. Yeah. Okay, so now it is done. Constraint is done. What is left? Let's go for load and boundary conditions. Similarly, I will give some simply supported boundary conditions on the 4 edges of the plate. So let it simply supported boundary condition. Okay. I can select this edge. Sorry, that's not. So I think all 4 edges are selected. Yeah. So let me provide the pinned condition. Yeah. So the plate is now constrained. Another is the impactor should be also given only Z motion, that displacement of impactor. So sorry, yeah, displacement. Okay, the step is initial, so that will give through reference point. So U1 is except U3, the remaining all 5 degree of motions are constrained, and the plate is impactor is only allowed to move in Z direction only, or U3 direction only. Yeah. Now, velocity of impactor should be given here using free-defined field. So mechanical velocity, free-defined field. So through the reference point, I'm going to give the velocity of impactor. That is 3, as we have done in the isotropic material in V3 column. Okay. So it is correct now. It's pointing towards to the plate surface. Now what is left? Meshing the part. So we have to mesh the part using the mesh model. Okay, so let me do it first. For 0, I'm only using the global mesh. As I used in the case of isotropic material, let me use 3 millimeter. That is not proper mesh size, but for simple analysis purpose, I am using it. Okay, so, and at the same time, the assigning material property for 0 layer. Okay, material property here, analysis is explicit, dynamic explicit, linear geometric order, and then this should be continuum shell. We cannot simulate it with 3D now because the material assigned is of the 2D type. So continuum shell selected. And then here, hourglass control also should be most of the time enhanced hourglass control we use. That helps us to control some spurious deformation that comes through the analysis process, and the element deletion. So we can give element deletion also to remove those damaged elements, not to interlock each other in the case of during analysis. So we can also give element deletion, yes, enhanced hourglass control, yes. So now our element is SC8R, 8-node quadrilateral in plane general purpose continuum shell, reduce integration with hourglass control, finite membrane strain element is selected now. Okay, so similarly for 90 ply also. Okay, for 90 ply also, mesh it. Yes. Okay, the continuum shell explicit. Okay, again for interface, the mesh density is the same. Let's take same mesh density or element size, and then the material type or element type for interface layer is not continuum, but it is cohesive. So we have to select this cohesive. And then here element deletion select yes. Then finally we can get cohesive 3D8. COH 3D8, that is an 8-node 3-dimensional cohesive element, or this element is selected. Okay, now done. And also we have to mesh impactor also. Impactor should be meshed also. Okay, and no need of assigning material property for impactor. Now this is the meshed assembly of the finite element model. So what is left? We have to run this model. Okay, maybe running this might take longer time than what we have done in the case of isotropic plate. In case of isotropic plate, it, but now because of the complex interactions and materials, it takes very longer time that maybe I cannot give you the answer of this one immediately. So let's create the job. Okay, so this impact simulation, let me say. Okay, continue. Then here also we are not using the user material, so directly we say okay here. So we can get this job manager dialog box. On that, we can either submit a job or we can check the job. So let me directly submit job and see what is going to happen on that. So if there is any mistake in my steps, at this moment, the system will immediately generate error message and show me where I made mistake, and I have to go back and see the source of error. So if it is okay, it will successfully go for running. Maybe this thing is running. That means what the steps I used are correct. Okay. There is no error message. There may be many warnings which are coming from a different case. For example, some of the warnings are R3D83. That means rigid body impactor element. The output request I asked for plate is not for the impactor. So that kind of conflict will come. Okay. So many conflict warning, which are harmless warnings, are there. So that can be accommodated.
Hello, Samit.
So yeah.
Samit, I think we will take the 5-minute break.
Yeah. Okay. That's okay. Yeah.
Okay.
Yeah. Okay. Thank you.
Yeah. You also take the water and all these things. Then
yeah. Sure.
Yeah.
Okay. Thank you. So we can continue actually.
Yes, Amit, please continue.
Yeah, okay. So it is now running, but it takes a lot of time. And also one thing which I realized is I moved Impactor to some distance above the plate. So I have to bring it to the, okay, it is no problem, but initially it takes sometimes simply moving Impactor towards to the plate surface. So let me kill this running, because you see 9, kinetic energy 9, total energy 9, repeating. It will continue for some times because the impactor is not directly coming into contact. It is above the plate surface, 1 millimeter up. I provided 1 millimeter up at the very beginning. So let me bring, approach it to the plate surface. So let me kill it here. Yeah, yes. Yeah, so the process terminated by external request. That is the warning, because I requested to terminate the process. So let me go to assembly, bring the impactor near to the plate surface. That it was in -0, 1 position. I place it, so let it come to 0, 0. That is correct position. So let me save it and run it again. Job. So submit. So while this job is running, let's discuss on some issues. And let me go back to my slide. Okay, let me share it with you. Let me share the slide. Okay. So this session criteria and other thing all are already implemented. Okay. Sorry, this thing is somehow disturbing. Anyways, so this session criteria for inbuilt Abaqus system is already what we have defined and described. These are the parameters which we introduce to our analysis. This is the damage evolution criteria, damage initiation and damage evolution criteria. Okay, so for these are also what we have discussed. Already we discussed these all points. Okay, that assigning material, assembling the parts. Okay, again defining the different simulation steps and output parameters. Okay, so these all are already done. So this output request also done. So for more information, I refer you to Abaqus user manual. which is there in the internet, section 4.2.2. So anyone can refer it for how we can implement output. Contact definitions. Okay. Load and the boundary, that already done. Okay. Okay. Okay, generating finite element mesh, already done. And running the file. So one thing that I missed is how to generate the Python code from Abaqus running. That at the very beginning, we start with the micro run. We have to run micros at the very beginning. That actually, the micro will help us to re-edit it and for other purpose, that like parametric staging on a single model. So that we didn't follow it from the very beginning anyways. Okay. So something very important in Abaqus simulation files, when we are submitting the job, Abaqus will generate a number of file types. Some of the file types in the morning session, my friend Sanjay explained them thoroughly. For example, how we can implement INP extension files. For example, if impact simulation is the name of the job which I submitted, then .inp is the extension. That is very important file, which is an ASCII file that defines the finite element simulations. Okay. So in that way, we can communicate the Abaqus system, that the graphic user interface system communicates with Abaqus finite element platform. Another .log file, .start file, .msg file, .dat file, ODB file, and these are some important files. As we run Abaqus, immediately these all files are generated in the particular folder or on which our directory belongs. Okay, so these files will help us for further. Even some of the file, for example, this INP file helps us to taking their copy to the Python script, and we can create the or rerun the file also. Okay. So other those ODB files are also very important file types. How we can visualize once our job ran successfully completed, then we have to see different outputs like the Abaqus, these hashing criteria outputs, the simulation output graphs, the counter plots, and different outputs must be observed. Also, we have to extract those things from our Abaqus file. And we can also change some graphics options. We can change also B-port annotation options, that the text file appearance. Okay, text file appearance must be also adjusted. Okay, so number of files are there. We can also make the XY data or manipulation of XY data also will be there. Okay, and based on my previous other works, because I expect that this running file will not easily complete soon, so that I want to show you the comparison between the metallic or that isotropic material, the result obtained for the same simulation for aluminum material as well as the composite laminate. in my previous work. That will give you a better highlight. So let me go to that. So these are some of the contour plots. For example, this is the U magnitude contour plot of the composite. Okay. For example, U3, U magnitude. Here you can see this is for aluminum plate. I use the same modeling approach for both of them. That's why I put them comma. And the values also are very different. For example, the U magnitude here, 8.5, 3 E minus 0.3. And here it is plus 4.659 plus 0.0. So very different. So the behavior of contour or the values are also very different in the case of composite and in the case of aluminum plate. The only difference with current work and this work is I didn't incorporate interface layer in this work. The remaining for 0, 90, 90, 0 plies are there. So whenever we incorporate interface layer, there will be also a lot of difference will come. Anyways, so this is the comparison between. This is also the von Mises stress in the case of composite as well as in the case of aluminum material. Okay, this is S11 contour, S11 contour. Okay, here S22 contour, S12 contour, and in the case of aluminum, we have no such damage. But for the composite, we have a damage case that Hashim fiber compressive damage, Hashim matrix compressive damage, Hashim. So this Hashim 4 damage criteria results are here for the composite case. And then the history outputs of the displacement versus time plot of the one of them. I took only one of them, so it is here. This is the energy graph. Actually, we have seen the energy graph from the previous aluminum material. So this is the energy graph. This is the velocity graph. Okay. And this is the contact force versus contact area versus time plot. And contact force versus time plot is also plotted here. Okay, this is actually not like this if it is properly simulated. Okay, and then for more information, I advise you to see some simulation works on the YouTube, which is I posted 2 YouTube Abaqus model for isotropic material alone, as well as for composite laminates also. You can refer those things with this YouTube channel. Anybody can see it. Okay, it is there on that. And also, I more refer you to Mr. Sanan work. That Mr. Sanan have a lot of works on YouTube. So he's very professional on this composite modeling. So that I refer you all to this thing. And actually, before going to do this, let me actually, that's already done by Mr. Sanjay, which I plan to show you how to run the INP file, how to run the Python script file, and how to implement UMAT. For that, let me open some extra Abaqus file. Let me do that. Maybe even though it is done by him, it is better to see that part. So let me share my screen to somewhere. Okay, here it is not there. Okay. Okay. Actually, this is previously run Abaqus file. We can see some previously run Abaqus file of composite. You can see this is a composite plate of 16 plies. Look, this is consisting of 16 plies. 1, 2, 3, 4, and it's a 16 ply in a model. Okay. I can better show you the result of this because that the previous one will not terminate easily now. It might take long time. Okay. So it is already run and the completed file. So let me open this. So result. Click on the result. Once the analysis completed, click on the result, and then you can see this actually rough meshing. This is done with rough meshing because the mesh density is not such attractive. Anyways, just to see the visualization of this. So how we can simulate it? We can simulate the impact. Okay. So this is U magnitude. So S is there. And here, the text messages are not clear. So we must make it visible. So let's go for the default annotation option for that. So on that, you can see this, this thing. So go to the state block and give the text what it is. Okay, font. So let's make it some 14. Okay, so you can choose any type of font from here. Let's see, Times New Roman font type. You can select any type of font, anyways. So let's take the default. So still it is not a good font. You can preview it. To easily visualize it, let's select New Time Roman. Times New Roman font actually. Sorry. This may be, yeah, it is very visible. So you can remove, for example, this, what do you call those? Either you can remove this compass, show trade, that tri-axis, show legend, show title block. There are title block here also. Show text and arrows. So these all options are there. So anybody can do that. Okay. And also similarly, we can see the history outputs here. Okay. All the history outputs are here. Okay. So for example, the kinetic energy. This is actually not the same some difference is there. The value of kinetic energy is 5.5, I think. It is not even 6. For less kinetic energy, it is done for less impact. That's why we cannot see damage on the plate here. Damage are not such easily visible because we have used very low energy. Even the displacement is incomplete here. Anyways, so these are the history outputs of this analysis. And then let me open some new database. Let me open new. So I want to show you with how to import the INP file. Only using INP file, Python file for some corrections, and UMAT file together. So let me implement it, because creating the model takes a lot of time. So I will take the INP file as the model created. This is for open hole plate type. For a plate with open hole, modeled with 1/4 of 1/8 of the model because of some symmetry. Okay, so set work directory. Let me go to the particular directory of this thing. It is there in this thing is there in Abaqus tutorial. So I placed it in here only. Okay. So file, now I want to import geometry. So how can I import the geometry? File, import, model. Then here, sorry, I am not going to import model from CAE file, but with INP extension file. For that, it is here, the INP file. Look, this is for fiber metal laminate case, which is online available type, which is there. So I select this. I took it from online for this, just for teaching or learning purpose. Okay, okay. So now the INP file will help us to generate the model. Yeah, so this is the model which is created with INP file, and then I'm going to incorporate the Python script for this. Okay, some of data are not, this is not full data, maybe part is there. For example, you can see parts, deformable 3D part 1, part 2 is there. So we can see some materials are there. It contains aluminum material, cohesive interface, and composite. So it is fiber metal laminate, FML case. So material is there. So let me incorporate the Python script to this file. So let me go to file, run script. Now, not export or import, but it is run script. To generate Python script, one thing I ask excuses, if we are going to generate Python script, we create micromanager, click on micromanager, then say create, and then give the name of your Python script. That will come with py extension. .py extension will it will come later in your analysis. So what you can do, for example, let me say impact. Okay, impact simulation simply. Impact simulation. So every time if you create this micro run, then you can get at the last the Python generated code. For that, all your steps must be clear and perfect. If you make some mistake, that mistake will be incorporated to your model and will not run precisely in the next running case. Anyways, now my intention is not to generate the Python script, but to implement the Python script. So how I can implement? Run script, okay, file, okay, go to run script, and then here the file filter or the file is py type, Python script py type. So that is there in this model. Yeah, this .py. This is the file. So then select it. Okay. So it is now running. The Python script is running. So yeah, now the model is now complete, and what we have left is we have to incorporate the UMAT code, which is created by Fortran coding. So where I can incorporate that UMAT code, I'll go to job. Okay, directly to job. I'm not creating anything. Everything is done. Geometry is done, material done, interaction done, steps are done. So I'm going to the this material. Before going to job, let me go back to property, because these materials are there in the property. For example, this is for composite. Let's click on composite, edit. When we are editing this composite thing, we can see the deep variable, state dependent variable, deep var 10 and 0 is given. Okay, number of solution dependent state variable 10, variable number controlling 11th deletion. 11th deletion is not given, that is 0. And the user material, as I told you, user here. So that user materials, all the composite properties are youngest modulus in one direction, youngest modulus in two direction, in three direction, and the Poisson ratio in 1 to 1 to 3, and other parameters. All composite parameters are provided here in the material subroutine, and which is directly linked to there in the script or in the UMAT code. So let me go to job, and here job is created as this thing. This is the job name. So let me incorporate the UMAT. So during this time, look, I have to click on general here, and then user subroutine file option is there. Click on user subroutine file. Then in my particular folder, I have two options. No, not two options, but materials are there. Hashing failure criteria, that is another. It is not this one. Okay. Here I can get the 4 or PY, and not PY, but F or 4 extension. In some computers, it works with UMAT.F only. In my computer, it allow me to use 4, Anyways, my computer is not integrated with Intel Fortran compiler because this program to run Intel Fortran compiler is required. Okay, so I select this. Okay, okay. Now we can run this file, but there is no Intel Fortran compiler in my system, so that the system will not run because it will abort with error or complete with error. So this is all about in my side. So if any question or suggestions are there, you are welcome, please. Sabra?
Yes, Amit.
Yeah, any question?
Yeah. Samit, please open the chat box. There are several questions. Please open the chat box. Okay, from the bottom side, from your Zoom. Stop the screen sharing, and then you will visible the chat box.
Okay.
There are some questions. We will take 2-3 questions, and then we will end the meeting.
Okay, let me see.
Yeah.
So some will not assign any section to the impactor. Actually, this week took rigid impactor. For rigid impactor, no section is required. That's why. Okay, Sarat already specified the answer. Thank you, Sarat. Impactor is rigid body, so that we need not require. Yeah, correct. Okay. What is the use of status in field output? Yeah, that status helps us to generate all the requested outputs. So whenever status is on, then our requested outputs will come to our final after the running of the program. Okay, okay. Yeah, Sarat, I thanks a lot. Okay. Don't we two elements in the thickness? Don't we have 2 elements in the thickness direction? Will it affect the result? No. Even if there is 2 elements in through the thickness, that will give us a better result. And the effect in the result is it improves the result, but it increases the simulation time too much. Rather than that, it has a positive effect. I think job is not yet submitted. Yeah, I already submitted it. Is it yet? We can keep more than 1 element in the thickness. That is, yeah, Sarat, thank you. Sometimes we get warning that are excessive element distortion. Yeah, this excessive element distortions are happening in running Abaqus. Whenever we are using coarse mesh size, and also if the material property is weaker, which cannot accommodate the amount of energy, then such problem will come. And it can be eliminated using proper material type and using a smaller discretization size at critical region of our work. Okay. Can we save this impact animations as video file? Yeah, we are using it. We save it for a very short period, not like long period, but we can make it slow to prolong the animation moment. By that, we can save it and we can use it for further. Thank you very much, Mustafa. Okay, so how would we calculate the average value of nodes? And node calculation is not included here. it is based on our mesh size that and the element size actually. Okay, so whenever the number of elements increased, the number of nodes also increase together with. So that's why. So this is all about Sabra.
Yes, sir.
Yeah.
Yes, Amit. From the Academics and Career Council, I thank you for this wonderful and excellent session on the Abaqus CAE. Hope all the queries are clear from the audience side. So thank you so much. So if anyone have any queries, then you can ask directly.
Yeah. Okay.
Some questions still, so 1 or 2 questions are remaining, sir. Can you just check it in chat box?
Which
Okay.
question, for example?
Yeah. If our result are mesh dependent, then what is the solution?
Yeah,
Yes.
results are all the time mesh dependent, because whenever we use finer mesh, that means obviously we are getting a very good result in finite element analysis. In addition, the problem of using that finer mesh is higher computational, it needs high computational effort of the computers, as well as higher computational time and the cost. Except that using finer mesh is welcomed. Okay, so and it has a lot of effect on result. Whenever we use coarse mesh, that the result is rough. Whenever we use finer mesh, the result is nice one. So that is always there.
Sir, actually, I have read in literature that if the post-failure region, the post-failure graph is affected by the mesh size.
Correct.
Like softening region that is affected by the mesh size. So we take some characteristic length into this I don't know, into this Abaqus somewhere, I don't know.
Yeah. So that characteristic length is also related with the incremental time, and also it is related with the wave speed of the on the element. So because of that, always there is an effect on the mesh size. So for that, we have to use a proper mesh size, and we have to calculate also the incremental time. Especially when we are using in Abaqus Explicit, incremental time delta t is and the characteristic LC also relate with the material properties like densities and the Young's modulus of material, and also with the Lamis constant, that lambda and what we call those two Lamis constants. So these variables affect our results actually.
Okay.
Thank you,
So,
sir.
any other questions from Ravindra? Any other question?
No, sir. Thank you, sir. Thank you.
Okay. Thank you, Samit. Thank you, Samit, for the wonderful session. Okay. So, can I end the meeting? Yes.
Okay.
Okay.
Yeah,
Thank you.
Thank you.
Okay. Bye.